but the foam, carbon foam, came into existence through a patent, US patent. Here we'll discuss a little bit about the raw materials synthesis process and the parameters which affect the foam formation and then properties of carbon foam. Since this is a FDP program, so I thought of adding few basic information about the carbon foam. There are various wide range of raw materials from which these carbon foams are prepared. They can be divided into three main groups. What is thermoplastic polymer, thermoset polymer, and there are materials which are non-polymeric in nature. In thermoplastic, we have pitch, tar, and bituminous coal. These are used as a precursor materials. And then thermoset, you have a wide range of material like polyurethane foam, which we have used predominantly. I will get to know more about it. Epoxy, melamine formaldehyde, phenyl formaldehyde, sucrose. These are some of the thermoset polymers. And you have non-polymeric sources like graphite, CNT, graphene, some advanced kind of materials from which one can make carbon foam. Well, if you make carbon foam from thermoplastic polymers, it gives a good graphitization. Graphitization is very important, mainly because it all the properties are dependent on the graphitization quantity of the amount of graphitization the foam can have. So this is mainly because these thermoplastics are crystalline in nature, so they can arrange in a they can arrange into mesophase, and then that results in graphitic structure. Well, apart from the raw material, the foam structure and properties also depend on the process parameters that one adopts, like during the carbonization or graphitization, like pressure, the temperature, heating rate. This is very important, heating rate, and the foaming method. One should be very careful in adjusting or setting the heating rate. The heating rate has to be low, since otherwise the foam might result into collapse. You do not want a char, a carbon char. You want a stable mechanical, having mechanical integrity, integrated foam. So there are wide range of the processing methods. So all these processing methods can be divided into 5 classifications, 5 groups. So one is template carbonization, compression of exfoliated graphite, assembly of graphene nanosheets, blowing of precursors, and directly carbonization. I'll talk about a little bit more on this synthesis process, synthesis method. In the template synthesis method, a polymeric foam is taken, generally a polyurethane or melamine formaldehyde, and which is infused with a resinifying agent, external resinifying agent like perfluoryl alcohol or phenyl formaldehyde. And initially, as the foam was flexible, now once you resinify, it undergoes curing and then becomes rigid. And then it is subjected to carbonization at 600 degree, above 600 degree. Of course, that carbonization can go up to 3000 degree Celsius, resulting into carbon foam. So this is generally done in our atmosphere. Sometimes the polymeric foam is directly carbonized to make carbon foam. The next is blowing of carbon precursors. So here I pitch or bituminous, it's a thermoplastic polymer, is taken into a closed chamber in an oven, and nitrogen is infused Now this pitch is a thermoplastic, so it doesn't contain any pores in it, unlike the polymeric foam. So this nitrogen actually is used as a blowing agent. So now the bubbling happens because of the nitrogen gas which is infused by pressure. And then this results to a polymeric foam. And finally, after carbonization, this results into carbon foam. Next, compression of exfoliated graphite. These are quite specific in the sense that here the precursor is natural graphite, which is subjected to acid treatment, resulting into acid treated graphite, and then thermal exfoliation lead to the delamination of these layers, and finally it is compressed, compacted to prepare carbon foam, because here you don't require carbonization because the initial material itself comprises of carbon. Similarly, the graphene nanosheets, assembly of graphene nanosheets, here again the precursor material is natural graphite, which is subjected to the popular Hammers method to prepare graphene oxide, and then graphene oxide undergoes a hydrothermal mediated process, and after freeze drying process, this can you can prepare a graphene foam, or alternately you can also call as carbon foam. So here also you don't require carbonization mainly because this the initial material is carbon itself. Well, we need to understand the crystalline structure a little bit before going to its properties. So how the temperature affects the crystalline. As you can see, the left hand side curves are the carbon foam, that of XRD of carbon foams. They are carbonized at different temperatures. And then one which is carbonized at 350 degrees Celsius, you can see it has a semi-crystalline kind of nature, amorphous or semi-crystalline. Further, if you increase to 1000 degrees Celsius, then also you can see, let's say, amorphous mostly, or semi-crystalline, you can say. But once the carbonization temperature exceeds 2000 degrees Celsius, 1500 or particularly 2000 degrees Celsius, then a peak corresponding to the graphitic structure, 002 plane of graphitic structure emerging can be seen prominently. So sometimes the temperature when it reaches the carbonation temperature is above 2000 degrees Celsius, then we call it graphitization temperature. So they are interchangeably used, the carbonization temperature and graphitization temperature. When temperature is very high, then we call it graphitization temperature. So the correspondingly, you can see the Raman's shift at different temperatures, and you can see the D band, which is attributed to the disorderness of the graphitic structure getting suppressed as you increase the graphitization temperature or carbonization temperature. So the foam becoming more crystalline in nature or having more graphitic content in it. The mechanical properties are very important of this kind of foams, mainly because most of these carbon foams are highly brittle in nature. So compression strength, compression here uh, in this image inside the image, you can see there is a foam which is without a polymer sheet between the platen. There are two platens. Between these, the foam is placed, and there is no polymer sheet between this platen and this foam. Whereas in the right hand side, you can see there is a polymer sheet between this platen and the polymeric foam. So that small change, polymer sheet in between, uh, influences the shape of stress strain curve significantly, as you can see. So what happens is mainly because this foam is highly brittle in nature. So there is a friction between the platen and this foam, and that gives rise to crushing of this foam, resulting into lower tensile compression strength initial uh, at initial strains, and that then it increases. And here it increases from one curve to another curve. It is mainly because the density. As the density increases, the compressive strength increases. That is the characteristics of these foams. Okay, the other end, the right hand side image, you can see that these stress strain curves are well defined because now the stress is directly transferred from the core of the foam rather than the surface, because there is a polymer sheet between this platen and this foam. Okay, so the compressive strength depends on the density of the foam, as you can see from these curves. And of course, the compressive strength also depend on the graphitic content, the precursor material from which the carbon foam is made, cell structure, strut strength of the foam. So it is quite complex. It depends on so many parameters. I've given few common properties of commercially available carbon foam, and these are the commercially available foams which are produced by various industries across the world from the raw material from which they are made. Like, for example, this ultra matte RBC is made from polyurethane, phenolic resin, and there are various kinds of raw materials as we have discussed. The densities are also quite wide because of the processing method. So each company or each industry have their own processes. So they produce a wide range of density materials. As I said, the thermal conductivity, they are thermally insulating materials, but by depending on the density, the thermal conductivity might change. So that is why also you can see a wide range of thermal conductivity values. Compressive strength again are wide, a big range, depending on the density, depending on different parameters as I have discussed a few minutes before. Tensile strength is not that popular because these are highly uh, brittle materials. Generally, tensile strength is not conducted, but still some of the companies they have presented. Of course, electrical properties I have not mentioned over here, but they are electrically conducting. The conductivity is in the range of about 1 to a 1 order of magnitude higher Siemens per centimeter. The foam that we prepared, we got around 0.1 Siemens per centimeter. I'll talk a little bit more about this. These foams are used in wide range of applications that include metal slag filter, cathode emission, electromagnetic interference shielding, microwave absorption. Being conducting, electrically conducting, they are used as electrodes in batteries, supercapacitors, microbial fuel cells, oil water separation, biological scaffolds, catalyst support, water remediation, and many more. I've given few futuristic areas like structural panels, for aerospace and aircraft. These are our forecasts, in fact. And they are already being used in thermal energy storage, lithium-ion batteries. So you can see the promise of these carbon foams and their wide range of applications. I've given few literature highlights, particularly in this slide. I have compiled EMI shielding properties only. Well, carbon foams are prepared in the for the first time in 1964, and since then onwards, there are a lot of literature you can find in patents as well as in scientific literature. There is a journal called Carbon, which exclusively publishes papers on carbon foams and many more. Well, that's where the progress now, due to the emerging the nanomaterials. So people have uh, expanded this carbon foam towards this nanotechnology. They have incorporated various nanofillers, and that's exactly what I wanted to give you the message here in this slide. You can see this particular paper talks about multi-wall carbon nanotube incorporated carbon foams in the range of 0.5 to 5 weight%, and they found significant improvement of EMI shielding properties. In another example, you can see Magazine, which is relatively a new material which is discovered or prepared in 2011. So this also shows improvement in shielding effectiveness or EMI shielding properties. Then people have used a wide range of nanomaterials like silica, graphene oxide as fillers to improve particularly EMI shielding properties in this case. As I said, they are also used in supercapacitors batteries, and here I've given few examples. This is a carbon foam made from melamine formaldehyde. This MF stands for melamine formaldehyde, and subsequently it was carbonized to make this carbon foam, and then they have coated with the nickel cobaltite nano sheets on top of it, and they found very interesting results, the electrochemical results. The nickel cobaltite, which is used as a active material in this kind of foams, that gives the required charge for the properties, electrochemical properties, charge storage. In another example, you can see this foam is made from PU sponge, polyurethane foam, and they've coated with the carbon nanotubes, followed by carbonization, and then again nickel cobaltite coating. And they found the capacitance of 1618 Faraday per gram at this density. Well, actually, our journey started sometime back when I was a PhD student at IIT Bombay. Um, we have done uh, in 2007. We started our carbon foam during that time, and yeah, what we did is we incorporated nano clay, Montmorillonite clay, into this carbon foam. The Montmorillonite clay was dispersed into polyurethane foam, and subsequently that was carbonized. And the objective here was to control the pore size or cell size and improve the electrical property. Now one can ask that clay, this Montmorillonite clays are generally electrically insulating materials. How that is going to improve the electrical conductivity? So what we found is that when we incorporated the nanoclays into the carbon foam, it has reduced the pore size significantly. As you can see, the PPI, pores per inch, increases significantly with the addition of the nanoclave. And that resulted into high density foam. The density increased, and the volume resistivity, the specific resistivity decreases. So that was our uh, aim, to reduce the pore size and to improve the electrical properties. Of course, we have carried out a wide range of, we have evaluated a range of other parameters like open cell content and cell window area size. So this has different attribution to the foam properties. So I'm not going in very detail. So coming to our next work, which is a recent one. Here we have grown this needle-like nickel cobaltite magnetic nanoparticles onto this carbon foam. And the objective was to improve microwave absorption property of the RBC foam. Okay, now I interchangeably, I sometimes I use carbon foam and then RBC foam. They are one and the same. Reticulated vitreous carbon or carbon foam. Okay, so please don't get confused with this RBC and then carbon foam. The idea of coating this nickel cobaltite is based on the literature, but of course the difference is we try to grow needle-like structures. Okay, so before coming to the work, I would like to give you a little bit of basics about the electromagnetic interference shielding and microwave absorption for the people who are not aware of the topic. Well, I don't need to mention that the importance of the electronic gadgets and the 5G and the recent advancement of other electronic components, gadgets. So because of that, it produces a lot of electromagnetic interference pollution. And that is also arguably have adverse effect on the human health. Of course, it is not proven scientifically, but studies are going on. So in that sense, for these two things, EMI shielding materials have importance. The EMI shielding materials, they actually block this interference, the electromagnetic waves, which are coming out from different sources. Traditionally, metals are being used. They are good EMI shielding blockers. They can block. But the problem with metals, they reflect most of the EM waves. You know, this is the simple mechanism. The EM wave, the incoming wave, either it will reflect back or it will be transmitted, some amount will be transmitted, and some amount undergoes multiple reflection or absorption. So what is most desirable is the attenuation of electromagnetic waves by absorption. So that is where the polymer composites or nanocomposites come into rescue, that these materials show good absorption properties, electromagnetic absorption properties, and that they convert this electromagnetic wave into heat or by other means. Well, 10 dB shielding effectiveness indicates that it blocks 90% of EM waves. And for commercial application, generally 20 dB is used. So something, if you get the value of 20 dB, that's good enough for many applications like your mobile phones or maybe the laptops. And of course, the defense and space requirements are more stringent. But what is required is you prepare a material which has more absorption domination. Well, this is the schematic by which we prepared this nickel cobaltite coating. Here you can see this is the PU formation, polyol isocyanate. It's a very simple reaction, and polyol contains all the ingredients like catalyst, surfactant, blowing agent. This this reactive mixture is directly poured into the mold, and then the PU foam is removed, and the PU foam is now carbonized. Here I have missed few steps which I will be talking later. And the carbonization is done at 900 degrees Celsius for 3 hours in argon atmosphere. And the heating rate was 3 degree per minute. As I said, it is very important. And it is treated with piranha solution because the carbon foam is inert in nature. So we require to impart some functionality into it. And then the hydrothermal reaction to prepare this nickel cobaltite coating. And this is the hydrothermal process. We take this is a known method, of course. Nickel nitrate and cobalt nitrate urea was used as a reducing agent. And the density of foam that we obtained was 0.28 to 0.37. Again, it depends from batch to batch sometimes. The treatment of piranha solution, it imparts few the organic polar groups, and it also reduces the water contact angle. The foam now becomes hydrophilic from hydrophobic 107. Here you can see the the morphology of nickel cobaltite. This is how they look like needles. And we have carried out the coating for different time periods, and what we found that the foam which was coated for 12 hours gives the highest amount of nickel cobaltite on it. We have carried out several characterizations of this coating. This is the extra diffraction. You can see all the peaks of nickel cobaltite present in the coated carbon foam. And the ID by IG ratio showed some increase indicating disorderness. And here also you can see by that nickel oxygen and cobalt oxygen peaks emerging. And the magnetic characterization also shows a hysteresis, small hysteresis of the coated foam. Yeah, this is important. This is what we wanted to achieve, the absorption. This is the SCT, that is shielding effectiveness, the total shielding effectiveness, which increased from 23 dB for pristine RBC foam, the uncoated, to coated about 36. Of course, these are the conservative values. We have performed the experiments on several times. So what is important, as I was mentioning, the absorption. So here you can see the shielding effectiveness due to absorption also increases. And though the absorption is not significant, but we get a invariable increase with the coating time. We try to understand the mechanism of the microwave absorption. For that we have carried out magnetic permeability and then permittivity uh, experiments, measurements. I've not given the entire results, Here you can see the dissipation of magnetic permeability. The uncoated foam doesn't show any dissipation, whereas the coated one shows. So, which is, of course, which indicates that it has contributing. The magnetic materials are contributing significantly to the absorption. And then, of course, the dipole polarization, the interfacial polarization because of the heterostructure, and the multiple reflection because of the pore structure and the eddy current loss are contributing to the absorption properties. We investigated the stability of this coating by ultrasonication. What we did, we took the foam and then dip into various solvents, water, acetone, ethanol, ultrasonicated for 1 hour, and we observed the color of the water. Now in water, there is no color change indicating the coating is stable. But in acetone and ethanol, we found some change in water, the solvent, indicating that some amount of coating material, nickel cobaltite, is delaminating from the surface, which is again corroborated by the Emi shielding of is before and after ultrasonication. You can see in case of water, it has not changed much, whereas in case of acetone and ethanol, it showed some decrease, but still this decrease is not significant, or which is almost above 20 dB, and which still has um, importance from commercial application, even if you treat with harsh solvents. We have measured these compressive properties. What we found is the coating has not really affected much on the compressive strength as expected, because the coating material is not contributing to the load bearing property. And here what we did, we have taken several density foams having different densities, and as expected, the strength increases density with the modulus. We have done some initial studies on the supercapacitors with the same foam, with the same image as you can see over here. And here we prepared a symmetric electrochemical cell where the electrode, negative electrode and positive electrode, both are nickel cobaltite coated RBC foam. And these are our results with the CV measurement, and this is gravitational charge discharge measurement. And we found a specific capacitance of 18 farad per gram, which is comparable to that of literature, but we are hoping to improve this value further. This work is still going on. In fact, these are some of the preliminary results that I'm showing. The next work is super hydrophobic coating on carbon foam for oil water separation. So this is a recent work, and we got a patent granted on this. The objective was to coat silicone oil onto this carbon foam by thermal deposition or vapor deposition to prepare super hydrophobic foam. And this work is in fact um, inspired by this paper, which is published sometime in 2008. So here what they have done, they have taken PDMS, polydimethyl siloxane coupons, cross-linked polydimethyl siloxane, and then coated onto some fabric. Of course, this is not on carbon foam, but some other. So we thought why not start with silicone oil rather than taking the cross-linked polydimethyl siloxane. So that's what our innovation. And here is the process of the foam and then Of course, I have already shown this process. And here, as you can see, this is what the coating method. So we have PDMS oil or polydimethyl siloxane. It's a silicone oil, which you found in almost all the laboratories that we use. And the foam is suspended on top of it, and this entire unit is kept inside a furnace. And we have coated at different temperatures. And this is how the morphology looks like after we coat the foam. These are the foams which are uncoated. You can see the surface image clearly. Now coated for different time periods, and you can see the continuous coating, and there are some flower-like structures. In fact, these are seated on a continuous silicon coating, which can be clearly indicated from this silicone mapping from EDAX. This is very interesting, very important result for this work. What we have done is we have coated at different temperatures, and out of this we have obtained the best results at 320 degree of coating. So the value reaches the water contact angle, which is a measure of hydrophobicity. It reaches 150. Then the contact angle slightly decreased with increase in further coating temperature. So we taken our further experiments at this temperature, and we have varied the time here, 5, 1, 5, and then 14. And we saw that the hydrophobicity or water contact angle increases with the coating time. And the maximum water contact angle we can reach up to 170 degree. That's quite remarkable. We try to understand why that temperature is important, T20. That's where we get the maximum WCA, water contact angle, or higher hydrophobicity, super hydrophobic. And we did the FTIR coupled with TGA experiments. And what we saw that this is what the DTA curve. So the onset of degradation is about 320, and it reaches a peak of 380. So when we did the coating at 320, we obtained the highest value. So we relate this result to our coating temperature. So further increase in temperature did not really improve the properties or hydrophobic properties. We also did water contact angle measurements, sorry, oil contact angle in this case. And we found super oleophilic behavior. As you can see, within a few seconds, the foam is completely absorbing the oil, silicone oil as well as engine oil. And here is the foam which is treated with the various acids and alkali to see the stability of this foam. And what we found that due to the acid treatment and the alkali treatment, the WCA decreased as moderately, but still it is in the super hydrophobic range. The WCA values are above 150. We've also done repeatability of this oil water separation by taking a wide range of solvent and oils, chloroform, DCM, and the percentage absorption depends on the density of the solvent as expected, because the pore size or the pore density is constant. And oil water efficiency, in fact, was not affected up to 10 cycles of adsorption and desorption. And this is the snapshots of the continuous all water separation by gravitational method. Here we have uh, added the oil water emulsion, and then with time you can see you have only water at the bottom, and the engine oil which is colored remain at the top. If time permits, then I can show you one video. I hope it will come. I hope you can see the video here. Dr. Bibu, is my screen video visible?
Yes, yes.
Yeah, thank you. So you can see this is the emulsion, water and engine oil. And I'll just fast forward it. Uh, Due to the light, you cannot see the water here at the bottom. The foam is placed, the coated foam is placed here in this funnel. Now you can see the level decreasing. Okay, so the water flowing and the colored substance, that is the engine oil, remains at the top. Okay, I have one more video that I just wanted to show again. This is water which is colored with a blue dye, and in the bottom you have chloroform, and you can see this floats on the top, and you have to forcibly put into the bottom. And now you can see the it takes the chloroform and it remains at the bottom. And then it instantly take the chloroform. We wanted to show it takes only chloroform, not water. That's why we again put it in a tissue paper. Now you can see that the tissue paper is not colored. Had it absorbed water, then it would have shown some blue color because the water is dyed with the blue color. Well, that's all about the oil water separation. Coming to my next topic is use of fume silica. In this case, we have used fume silica to improve the microwave absorption properties and EMI shielding in the carbon foam. So here what we have done is we have incorporated the fume silica into the isocyanate, one of the components of polyurethane, that is methylene diphenyl isocyanate. And you can see the stability of the fume silica in the isocyanate. Um, these are the percentage that we have added, the fume silica. They are all they are commercially available product, having a particle size about 14 nanometer. And what we observed, this suspension or dispersion, the viscosity of the dispersion increasing exponentially with the addition of the fume silica, mainly because they have huge surface area. So that restricts one to or, optimize the percentage of fume silica that you add. You cannot add high because probably later you will not be able to prepare pure foam so easily once the viscosity is very high. So one has to keep the percentage low, about below 5 percentage for weight percentage. And this is the same process I have already shown you several times. This is just for completion. And yeah, fume silica is dispersed in isocyanate, and the rest process remains same. Here we prepared two different densities of foams, and here you can see the SCM images. And as the density becomes high, then the pore size also uh, becomes smaller. And here we have quantified from these images. So the higher the density is, smaller the pore size. We have characterized these foams incorporated foams by X-ray diffraction and Raman spectroscopy. From XRD, we don't find much information, mainly because the fume silica is also amorphous, so not much information. But from Raman spectroscopy, we can see that the ID by IG ratio increasing slightly, indicating the disorderness of the foam increasing. Rather, it's decreasing in this way. The blue color is the one which is having the highest percentage of fume silica. Thermal properties we have uh, investigated through TGA, and you can see both the char yield as well as onset of degradation temperature increasing significantly with small amount of this fume silica. We have carried out electrical conductivity for the foams, different foams. Of course, if the density is higher, then the conductivity is higher, obviously. And what we found that with addition of fume silica, the conductivity has not decreased significantly. We were of impression that fume silica being inert, sorry, electrically insulating material, it might decrease the conductivity significantly, but that did not really happen. We have measured this EMI shielding by taking two different foam geometries. One is big and another is small. This is fitted into this waveguide, the size of waveguide, and this is bigger than the waveguides. There's a purpose why we did this. And yeah, sorry for this busy slide. I have put so many results into this, mainly because it is easy for me to explain. So here you can see the density, the foams having this density range and then this density, and the foam which is small in size and then bigger in size. What we found, so without spending much time in the results, I directly come to the conclusion here that the density did not affect much on this EMI shielding property. However, the specimen size was found to have profound effect on the EMI shielding. So when we took bigger size foam, then it showed better shielding uh, property compared to the smaller one. So this may be attributed to the gap between the waveguide, because these are the foams, porous material. So the waves might leak into, or so that might be the result, the reason. Another important conclusion that we observed, which is very important, is the fume silica addition significantly improved the microwave absorption properties. So here you can see the right hand side images are SCA, that is shielding effectiveness due to absorption. So these are quite high values. And you can see the significant improvement in this SCA. So that is something very remarkable. Okay, coming to the last part of the presentation. Here we have used graphene oxide. We have incorporated graphene oxide into carbon foam for bone tissue engineering. This work we have done with collaboration with Dr. Nivedita Lenka of NCCS, National Center for Cell Science, Pune. And the graphene oxide was prepared by the conventional modified Hamas method. And these are the results. Of course, I'm not talking about RGO, that is reduced graphene oxide. This we have used for different other purpose. But what I bring to your notice is the graphene oxide, the characterization results. The objective here was to investigate the effect of graphene oxide on gingival mesenchymal stem cell growth of carbon foam. The carbon foam is a biocompatible material, but we wanted to increase the cell growth. Okay, so here we have done growth of hydroxyapatite by using simulated body fluid. We have dipped these carbon foams and then graphene oxide loaded carbon foams into simulated body fluid for 8 days, and then you see the hydroxyapatite growth by XRD and FTIR. Now even carbon foam also shows some amount of hydroxyapatite growth, but the extent of formation of hydroxyapatite is higher in terms in graphene oxide. Graphene oxide presence, and that can be corroborated by FTIR as well. This is the cell viability study by MTTSA, and here you can see the graphene oxide addition increases the cell viability. We did in vitro cell growth studies and osteodifferentiation of gingival mesenchymal stem cells. And here you can see the fluorescent images. They were stained with DAPI and tubulin. You can clearly see the graphene oxide added carbon foams showed higher cell growth, the MSC cell growth. And the same thing has also been observed by the optical microscopes and other techniques. So coming to the conclusions of my presentations today, the magnetic needle-like nanoparticles coating on carbon foam, nickel cobaltite coating, enhanced the microwave absorption and also imparted charge storage in carbon foam, which was used as supercapacitor electrode. The nickel cobaltite acted as a active layer there, active material. The vapor deposition of silicon oil produced nano label coating on top of carbon foam and leading to super hydrophobic surface, and eventually it showed efficient oil water separation. And nano-sized fume silica improved EMI shielding and EM absorption, more importantly, of carbon foam. And the last one is graphene oxide facilitated osteodifferentiation of mesenchymal stem cell on carbon foam scaffold. With this, I come to the conclusion of my talk, and I acknowledge the people who have worked hard. My PhD student, Kaumudi Yadav, Rohit Bagal. These are the people from who have done the work actually. Nivedita Lenka, Dr. Lenka, Dr. Manju Baher from NCCS, Dr. Ganesan from IGCAR, Dr. Subhanna Datar, DIT, and my colleagues Saurabh Parmar, and my funding agencies DIT and then SCRB DST. And of course, special thanks to Dr. Bihu Prasad Swami for giving me this opportunity to interact with the allied audience, the esteemed audience. These are our group members, Kaumudi and Devyans, Prakash, Rajkumar. They are doing PhD with me. Prakash is working in NMRL, he's a scientist there. Rajkumar is again working with DRDO. Rohit was project assistant. Sneha is a tech student. We have few facilities like small angle X-ray scattering, electrospinning, tubular furnace, hydraulic hot press. So I would invite all of you to like if you want to use ever or if you want to use any facility or have a visit, so please drop a mail or I'm open to collaboration. And thank you very much for your time.
Thank you very much,
And
Professor,
yeah, if any questions, I would be happy, of course.
regarding this interesting and innovative talk. Then I would it is open for the questions. Before that, I have a little bit some questions regarding this thing. So you have shown a nice video that how separation between the these two phases, well, and all these things, how can collect from carbon form.
Right.
Thing is that whether it is selectively collect some elements like arsenic and this mercury. So
Yeah,
yes,
that's a
in Manipur we have seen that the arsenic contamination is more. So whether it is can be useful so that this project can be, or there is some PhD student we can take to see that arsenic contamination in Manipur state, because it is a very means, emerging, dangerous conditions. So some of part of the arsenic is there. So I would request whether it is possible that the because of course, we are working with the RGO and other uh, materials to how the arsenic can. We are thinking of this thing, but is it possible that this collect arsenic contamination?
yeah, thank you, Dr. Bibu, for asking this question. Actually, it has a lot of social impact. I really appreciate that. Yes, I mean, we are also trying. So far, we have tried with other material, not carbon form. Presently, we are developing a membrane, polymer membrane with nanofillers again, mainly for organic dye and then heavy metal ion adsorption. But in this carbon foam, we have not explored that part. But that would be really interesting. We'll have to actually modify the foam accordingly so that it can catch this heavy metal like arsenic or any heavy metal. So that is very key.
Okay.
So of course, I mean this particular foam, the one which I have shown, the silicon coating may not be effective, but we will have to modify it with proper functional groups or some other material which can take uh, right the arsenic or any heavy metal ions. Yeah, in this case we haven't done, but
And
can be I think explored.
and second thing, second question is just information. Whether your small angle X-ray scattering is operational
Yeah,
now?
yeah. I think
Because
we
I
it
am
was work.
waiting
Yes,
for
yes.
a long time.
Yeah, it was working, but
Yeah.
recently we had problem with UPS. We have
Okay.
almost settled out.
Okay.
Hopefully, it will start in next week or so. I'll let you know.
Okay.
I'll talk to
Okay.
you
Okay. Thank you. Thank
for
you very
that
much.
later.
So,
Yes.
any more questions from audience? Please ask. That will better for your query and questions. I think there is no more questions. I should ask
Okay.
one information. So you are means hydrohepatitis HA. eh.
Yeah.
So that you said that it is your cell growth you have done in
Right. Right.
NCCs.
Yes.
So there is some, if we send these thing materials to Nivedita link, Dr. Nivedita link, it's possible to contact this information.
Yes. Actually, I will talk to her. Yeah.
Yes,
And
I
in
am
fact, I can
really
give her I mean details so that we can
okay.
also contact her. Problem.
So
In fact,
I am also, I am very much interested in bio because last few year I live because this there is some limitation of means working condition all
right,
these
right,
things. So
right. Yeah.
I
I am in
leave
fact
bio path.
eager to visit NIT Manipur
Yeah, of
at
course,
some point.
anytime
Yes.
after
Right.
pandemic.
Yeah, correct.
Okay. So because the bio part, I have the only material scientist we are doing something.
Right, right.
So
So that is the
let's
main reason. Actually, I'm lucky to get contact of her.
yes,
And
yes, yes,
yeah, we are because I'm not a biologist, so we make some material and then we
yes,
try
yes.
to get the
We
tester
are
from different
material.
places.
Let's see some exploration of
Correct,
means
correct.
some bio conditions. At least we should be multidisciplinary because nowadays
Yeah,
multidisciplinary
right,
and
right.
interdisciplinary is the new stage.
Yes, yes, that is the synergism. Actually, that is the
Yes, yes, that is
synergism.
the synergy. Yes, yes,
Mainly because see, if I prepare some carbon foam, if I keep it with myself, then it has no meaning unless
yes,
I go to someone for application.
yes,
And
yes. Thank you, thank you, thank you,
yeah,
thank you very much. Okay, I think there is no more questions from audience. So I close this session for the first session of the final day. And a thank to our speaker, Dr. Patro, regarding the very, very, very informative talk. And of course, he's welcome to NIT Manipur
yeah,
anytime
thank you
after
very much.
pandemic, if possible. So thank you very much once again. So
Okay.
the next talk is our my one of the good friend Dr. Mithun Roy. He will talk. His talk is from 12:15. He's more working on the these anti-cancer cancer application. I think most of participants are this many of participants are the bio related or biopharmatic or this. So I request everyone should join that. That is very very interesting lecture. At least you should do. Thank you very much. Up to 12:15. Then we'll talk. Meet the Dr. Mithun Roy.
Okay, Dr. Vibhu, I will log out if you permit me.
Yes, yes, please,
Yes,
please,
no.
please,
So
please.
thank you very much. Thank you
Thank you.
again, all the participants, for
Thank you.
giving your valuable time. Thank you very
Thank you.
much.
Thank you.
है फार्मेसी वाले का मसूद क्या नाम परिवर्तन क्या लाऊं बता। ठीक है करनी छोड़ दूं है करनी छोड़ दूं। इसमें क्या दिक्कत है। चेंज भी करेगी तो बढ़ जाएगा। एक्सप्लेनेशन तो ऐसे ही दिया तो एक्सप्लेनेशन से समझ में आ गया
for anti-cancer applications. So I request Dr. Mithun Roy to submit his PPT. Dr. Roy, can you hear me? Hello.
Now I can hear.
Now it's okay. Okay. Thank you. Thank you very
Okay,
much.
fine. Thank you. Thank you.
So before I would start the second session, let's introduce Professor Mithun Roy. He's MAC Master. Uh, sorry, he's a Master in Chemistry from University of North Bengal during the 2003. Then he did some research training programs in ISC Bangalore. Then joined as a research fellow in under the supervision of a Professor Akhil Kumar Chakraborty, Akhil Ranjan Chakraborty, at the Department of Inorganic and Physical Chemistry in Indian Institute of Technology Science, Indian Institute of Science, Bangalore. And after that, he has a couple of postdoctoral research associate and a research fellow at IIC Bangalore and the University of Heidelberg in Germany, then postdoctoral research fellow in Colorado, University of Colorado, USA. Then after completion of this postdoctoral paper, he has joined as a assistant professor in October 2014, and he's many projects, 4 projects from different agencies. In his administrative, he has associate dean, NIT Manipur, from 2016 to 2019. Then head of the department from 2018 to 2000. The member of governing body BOG NIT Manipur 2018 to 2000. Nodal officer TQ3 from 2019 to till date. So he has very experience in as well as in academics as well as the administrative job. So and now it is it is open for Professor Roy's talk. Today's talk is the photoactivable transition metal complex functionalized to gold nanocomposite for the anti-cancer application. Now it is over to Professor Roy for his this informative talk. So it is over to. Thank you very much, Dr. Roy.
So thank you, Dr. Bipul Prasad Swain, for a nice and long introduction. And so I am going to talk about the photoactivable transition metal complexes, functionalized gold nanocomposites for anti-cancer applications. So these actually the functionalization of the metal complex with the nanocomposites, it is very little explored, and the photochemistry of these things, nanocomposites, particularly with the metal complex, it is not very known. So actually we are interested to do some work in this area and try to explore some of the photophysical properties and whether we are interested, whether it is ideal for the anti-cancer applications or not. So so that's what I've designed. Some of the I have taken some of the work that is published from our group, and then I just summarized in a nice way and try to conclude the what will be the effect of functionalizing the photoactivable transition metal complexes with a gold nanoparticle, and for cancer applications, particularly in the photochemotherapy. Yes, hello, yeah. So I have divided my talk like this. So it will be general introductions on cancer scenario, okay, in the current world, okay, and then photodynamic therapy, and how the transition metal complexes have emerged as ideal photochemotherapeutic drugs instead of the traditional photodynamic drugs. And then some of the few aspects I think it is a very good faculty development program that is structure materials. I think what is the nanochemistry and all these things I don't have to explain too much. I just go with my these things. So but I have touched a little bit. So what is the nanostructure materials, and then their anti-cancer applications. So introduction is like that. Then I have prepared 2 different complexes. One is the iron 3 complex that is not actually functionalized into gold nanoparticles. Another is same iron 3 complex. It is a functionalist in gold nanoparticles. And then I have able to show. I will show you. This is how this strategy it is become ideal for the targeted photochemotherapy, that is for targeting the red light. So red light is very much essential for the photochem applications, because when uh, when a deeper tumor tissue is there, when some inside the tissue, if a light has to reach, it has to be red light. If we use the higher energy light, so it cannot go through, because the wavelength it matches with the pores and then cavities inside the cancer cells. So red light is a perfectly suited for photochem applications. So we are going that. Then second part, it will be a red light activable manganese carbonyl functional as gold nanocomposites. Okay, so here also similarly I have designed. One will be only manganese, one carbonyl complex, another only functional as gold nanocomposites, and then we will demonstrate how these nanocomposites can be a very good anti-cancer product and with the theranostic potentials. Okay, and then this lanthanum, particular the last one, the lanthanum curcumin functional as gold nanocomposite. Um, as a red light activable mitochondria targeting purity agent. So here I will show that normally the lanthanide complexes, it is almost like a calcium. Okay, so all complexes you will find it in a white color. Okay, so white color means it doesn't absorb in the visible region. So but when we attach this complex with the gold nanoparticle, then we have find it out it is a remarkable redshift. Means we got a complex, we got a nanocomposite that is absorbing around 700 nanometer. It is perfectly ideal. So earlier lanthanum complexes were not suitable for chemotherapeutic applications, but in this work we are able to show that if you functionalize with the gold nanoparticle, then you can achieve the target. Okay, then I summarize and then conclude. Okay, the first it will start with the national and the global cancer scenario. So you can see it here. So that picture you can show different regions how the cancer it is actually prevailing. Okay, so it is data is taken from taken in the 2018. Okay, and it is shown that that Globocan to 2018, the every 8 men along with the 11 women die in the by 230. Okay, one man in uh, one one person of the 8 men will die, and one of 11 women will die in cancer in 2030. So then it is there 18.1 million new cases and 9.6 million new deaths. That is the death is happened in the 2018. So this is a very scary scenario. So now we are actually struggling with the COVID. So but in this COVID research, one article I have find it out that cancer research, it actually there is found in the Nature, it is came, it is saying that because of COVID, so much focus it is given. So focus isn't out of sight from the cancer, but cancer is one of the most deadly disease. So somebody is having, and it is slowly increasing because of our lifestyle and other complicated parameters. So that is daily introduced in our life. So because of these things, it is cancer is very it is increasing day by day. So we have to work in this area. So now you can see the cancer scenario in India 1990, how the cancer scenario it was. Okay, per 1 million cases, then how India it is everything is blue. Okay, everything is blue where fewer yellow. Now almost all are yellow. So yellow is 75 to 89.9. Okay, and then some cases are red. So these places are more vulnerable for cancer. So 2020 it is increased. So now if you can imagine, so with the evolution of the human history or and the advancement on scientific knowledge, so almost all the deadlier diseases which past existed, so it is not almost it is almost not there. For example, polio. Earlier in 1980s, 1970s, polio is a very much predominant in the earth. Okay, in even in India also. But nowadays with the pulse polio, that vaccination, so now it is we are able to eradicate the polio completely. Now we are also look into that how the malaria can be controlled. Okay, malaria, dengue and other things that can be controlled, but it is controlled to some extent. But cancer, it is not controlled at all, but it is increasing day by day. Okay, so ICMR that gave the new data regarding the cancer, so estimated 12.9 lakhs. So all this data it is showing that it is very much we have to we have a lot of concerns regarding the cancer, and we have to deal with that. Okay, so and the data is showing that when it is a very horrible situation is coming in near future. Okay. So now the current cancer treatment modalities are like surgery. So surgery, what they are doing that when tumor is developed by surgery, tumor is removed, and then it is okay, then it is fine. So, but there is a problem. Uh, if it is not surgery is not done very properly or with a minute precision, then it will be a high chance of recurrence. Okay, but in a tumor stage it is fine, but when it become a malignant stage, okay, like in the last advanced stage, so this surgery is not a ideal process to eradicate the cancer. Then another process is the radiation therapy. So radiation, high energy radiations are given in the tumorous area, okay, where the tumors are detected, and with the because of high gamma ray, so these cancer cells are killed. But if it is not very specific and since it is a very high energy radiation, so there is a possibility of the secondary malignancy. So we are to going to treat the cancer, but again, my cancer may recurrence with these things. Okay. Then chemotherapy is widely accepted things. You know the cisplatin, okay, and other drugs like a Taxol, doxorubicin. So these kind of drugs are administered. So there are various kind of. So people are mostly working on the chemotherapy from the last 1960s. Okay, and to some extent it was successful, like a prostate cisplatin is very much effective against the prostate cancer cell lines, okay, and then breast cancer cell lines, some other chemotherapeutic drugs have been successfully developed. But cancer is a very tumor tissues, cancer cells are very intelligent enough to evolve themselves to become a drug resistant. So this is a big problem in designing the drug with the chemotherapeutic drugs against the cancer. Okay, and also the if it is not target specific, then it is also a problem. So then it also create a secondary malignancy along with the systemic side effects. Then immunotherapy, it is a new one. So they have to drug we have to administer that actually boost our immune system to kill the cancer cells. So it is a lot of research is going on in that. So, and this treatment, of course, it is a very expensive treatment modality, but some success rate is found in this area. So still some work is going on. So there may be the future um, prospect in this immunotherapy. Then there is a hormone therapy. Again hormones are actually it is given in some, particularly this has become successful in case of breast cancer cell lines. So but the treatment cost is very high, and so it is not feasible to treat the all different kind of patients. Okay, then stem cells transplant. So this is a new therapy. The stem cell is a cell, so from this cell you can grow any kind of organs. Okay, and this type of stem cells actually now coming up very slowly, and whether if it is able to replace the stem cell, then it is a future. So now stem cell can be collected from bone marrows, and then you have it in cord when the baby is born. So you can store it, and then you can have the treatment of this kind. Okay. So then there is a bone marrow transplant. So this is also again a very cost effective, no, not very cost effective, and therefore people are not opting frequently in that. Okay, then targeted chemotherapy, it is the must essential targeted chemotherapy. Wherever you just do the radiation therapy, chemotherapy, and then hormone therapy, this type of therapy, then these drugs has to be very target specific, means it has to be work only in the cancer cells. So a lot of work is going on in that. So we are also the focused our work in this area, and then try to see how we can achieve our target. Okay, so if you use the light, okay, let's say uh, now you are administering a drug. Okay, so you have taken the drug, it has gone to normal cells also. Okay, cancer cell it is more, because cancer cell have a probability of taking more and more drugs, okay, more and more foreign materials than the normal cells. Okay, now if you design a drug which is activable only with the light, and you shine the light particularly in the tumor area, okay, then selectively it can kill. The drugs will be activated only in this region, okay, and it selectively kill the cancer cells. Normal cells it will not be there affected, because your compound which is administered, it is not active in the dark. Without light it cannot work, only with the light it can work. So this type of modalities, it have appeared in 1980s. So it is known as a photodynamic therapy, where the porphyrin based drugs are used. Okay, and this treatment modality is more tumor specific and it is non-invasive. Okay, so particularly in the skin cancers and all these things, so these type of treatment are there. Okay, it is more probable esophageal cancer. Okay, so this type of, so but this type of therapy is also feasible, and now with the current advancement of the optical fibers, so they can take the optical fiber deeper into the tumor tissues and then shine the light selectively. So this type of advancement is already has come, but still a lot of work has to be done in this area. Okay, so now we are focusing on the drug part. Now we have to use a photosensitizer. What is there? Now you can see it here, the photosensitizer. Okay, you shine the light and take up, there is a, in the cell itself there is oxygen. So this oxygen can be transferred, can be transformed into a singlet oxygen, and singlet oxygen is very very toxic and it oxidizes the cancer cells. Okay, basically that cell membranes, some cellular proteins, that DNA materials and all these things. So all these can be killed by the singlet oxygen. So we are producing a singlet oxygen in situ in presence of photosensitizer and non-toxic light. Non-toxic light means there is a question. So I have mentioned that lower wavelength light, it means high energy light, it cannot penetrate deeper into the tissue. So there is a called PDT window. So it is from 600 to 800 nanometer of light. So these penetrate deeper into the tumor tissues very well. So you need that kind of light. Means your drug is should be activable only in this kind of, so 600 nanometer to 800 nanometer. So most of the organic drugs, if you see the lack of presence, lack of the chromophore or suitable chromophore that can be activable in a red light, so we have to discard it. So there is a few things are left. Only the thing is left is the porphyrins. So porphyrins, due to the extended, these are macrocyclic rings. Okay, so these macrocyclic rings, because of the macrocyclic rings and extended conjugation, so these molecules are absorbing light around 600 nanometer. That is called Q band. Okay, and if you excite these molecule in the Q band, so then there the photo process is shown here. So this photosensitizer, when you expose with the red light, the ground singlet state goes to the excited state. So these can be relate decaying to the lower singlet excited states. If from the lower singlet excited state to ground state it is happening, okay, some transitions, okay, then it is fluorescence, okay, like this. But sometimes there is some process in between, there is some triplet excited state. So through the intersystem crossing, it can be your excited singlet state can be relaxed into the triplet state. Now the triplet state to ground state, it is a decay from triplet excited state to ground singlet ground state. It is a spin forbidden process, and therefore sometimes it happens, it is not happening not like that, but the process is become very slow and we call it a phosphorescence. Okay, but instead of phosphorescence, if this triplet excited state transfer it energy to triplet oxygen, they can generate a singlet oxygen. Okay, so this is the chemical process, the where to from which a photosensitizer can be activated with a red light, and in presence of molecular oxygen, triplet molecular oxygen, through a type 2 photo process, it can be converted into singlet oxygen. So you need basically a merely energy of 1270 nanometer light, 1270 nanometer. So that type of energy it is having already, so you can transfer it very easily. Okay, and sometimes it is happened that this excited state itself, this excited states even itself, from the triplet molecular oxygen, it converted into the various kind of reactive oxygen species. Okay, so these reactive oxygen species again very toxic, and it can kill the cancer cells in a very fraction of seconds. Okay, so now different kind of photosensitizer are there. So what is the ideal photosensitizer? So it is given here: low dark toxicity and remarkable taxocycline in presence of light. So in dark, it should be inactive, in light, it should show some toxicity. A very major difference will be there. Strong absorption in PDT window, that is red to IR means near infrared region. Okay, that is what that is the primary criteria, because you need to have a light that is a more penetratable into the deeper into the tissue. Okay, and then high quantum yield of here it is singlet oxygen formation from the triplet oxygen. So that is also required, because if quantum yield is very low, then your activity will also be low. Okay, cytotoxic activity, and also the triplet set lifetime has to be very high. Then high chemical stability, it is of course, if it is degrade, then there is no use. So drug regulatory board, so actually they will not approve any drug which is can be degraded, which is can be degraded in the biological medium. So high chemical stability is required. Then you have to be synthesis has to be done, because if it is a involved a major like a multi-step synthesis, and it is a very low yield, then it take a lot of time. So that of those things has to be minimized. So short and high yielding synthetic route, obviously, and then it has to be soluble in biological medium. Okay, and low photo bleaching to prevent the degradation of photosensitizer. Okay, so photo bleaching means like a, if you excite it, then suddenly if you not enough time, okay, so it has to be photo bleached. If it is remain activated in the remain activated in the activated state, then it will start destroying your normal cells also. Okay, so and also the photosensitizer, if it remain for longer time, and there is a chance of that it will degrade. Okay, so this type of criteria it should be there. Lot of advancement from 1980s it is there. So photosensitizers for PDT applications are like a first generation, second generation, and third generation. First generation of photosensitizers are mainly the hematoporphyrin based. So these are molecules absorbing light and Q band, that is around 630 nanometer. And then because of lower solubility, and then low quantum yield of single oxygen generation, and then photo bleaching properties, so these are actually uh, uh, not become very ideal in cases. Okay, so you have to modify it. Then second generation photosensitizers came. It is some porphyrin based like this. Okay, so it somehow enhance the aqueous solubility, uh, but not enough in case of like a large differences in cytotoxicity. So and then non-porphyrin based are very important, because in porphyrin there is actually problem. So in porphyrin there is a biological pathways, normal pathways to degrade the porphyrins. There is a heme oxygenase. Okay, so they can degrade the heme or this porphyrin ring into a bilirubin. Okay, so bilirubin actually create a toxicity in the liver. So you know that it is called jaundice. Okay, so it is hepatotoxic. Okay, so porphyrins, no, it's normal. So you need to have non-porphyrin drug. So then this type of methylene blue, these drugs are used. So these are somewhat ideal, because it mm, uh, generate singlet oxygen with a in a lower energy, when it greater than 600 nanometer, high water solubility. Okay, and a high chemical stability. So to some extent it has. Okay, but still it is not sufficient. Then third generation photosensitizers came. So for example, aminolevulic acid. So so they have this type of molecule. This is a photosensitizer attached to a uh, this type of gold nanostructure material. So these are photosensitizing ability. So instead of so much advancement, so in spite of so much advancement, so there is a some limitations, because of when you synthesize the porphyrin, sometimes the porphyrins with the asymmetrical porphyrin, so these are very difficult to purify. Okay, so poor chemical impurity. Okay, so prolonged photo exposure, so they remain photoactivated. Okay, and then lead to a skin photosensitivity. So your skins become some reddish after the treatment event. So then it can create a secondary malignancy. Okay, Then biodegraded product is bilirubin, so that we have to get rid of. Okay, so we should not have the kind of any kind of toxicity related to the photosensitizers. Okay, so we have to come up with a solution so where those limitations can be minimized, and we can have a better photosensitizer for phototherapeutic applications. Okay. Now, what is the role of transition metal complexes in photodynamic therapy? So these transition metal ions, so transition metal ions have a facile redox chemistry. Okay, so metal, if you change the metal iron to iron 3, so they can very easily can be converted. Okay, um, facile redox chemistry that is achieved in the biological redox window. Okay, variable oxidation state and coordination number, so you can have plus from 0 to coordination number, even 11 12 higher number also. So ligand induced tunable geometrical properties. So if you just design a ligand, then you can change the geometrical properties. Then according to the ligand also can tune the thermodynamic and kinetic characteristics. And we have to focus only on some biocompatible metal ions, because copper, iron, okay, zinc, then molybdenum. So this type of metal ion is already present in the biological system, okay, to some extent. But if it is a more, then it will be very toxic. So that thing we have to take care of. So these are overall by some kind of biocompatible we have to take. So metals in medicine that is used because of this kind of properties, are chelation therapy. Then these are the obviously essential elements. Nature has selected some metal ions for their particular enzymatic reactions. Then of course drug delivery it become important, then it become a diagnostic agents, for example some gadolinium based compounds, and radiopharmaceutical technetium based compounds. Then of course these are become therapeutic agent. The people are using platinum, ruthenium, gold, iron, osmium, different kind of metal ions. Then of course a bioimaging. So and the metal complex is very important, now become very important in biotechnology and biochemistry. For example, fingerprinting. So you require a kind of metal ions. Okay, so there is a lot of scope, and we are now actually interested in doing that one. Okay, now how these metal complexes can be very important in photochemotherapy. Okay, now suppose for example if I take you 110 phenanthrene. 110 phenanthrene, it absorbs light only at up to 280 nanometer. So 280 nanometer light you cannot use for photodynamic therapy. Okay, but this 110 phenanthrene, if it is combined with the copper, okay, then it absorbs around 640 nanometer. So that is the advantage, and that is actually because of some DD transitions, or it can be a metal to ligand center transitions, or ligand to metal center transitions. So these metal center transitions like DD transitions, ligand to metal or metal to ligand charge transitions, these are very important. If they absorb the light in the visible region, then these can be used for photochemotherapeutic applications, because metal complexes in their photoactive, if you photoactivate them, so in the excited state they can undergo various kind of reactions that is still under investigations. Okay, so that is the thing. So I have just noted some of the salient features of having having transition metals complexes. For advantages for the photochemotherapeutic applications are they are absorbed in the visible to red light region. Okay, then heavy atom actually promote the very efficient spin orbit coupling, leading to high triplet excited states. That is mm, uh, they can from doublet states to triplet state they can produce it. Okay, singlet to triplet. If a metal ion promotes, metal ion is there, so there is a possibility of high spin orbit coupling. Okay, then generally very high yield of single oxygen generation. Okay, longer emission time and all these things are there. So these are advantages for having the metal complexes as. So these metal complexes are used. Okay, heavy transition metal complexes are divided platinum, ruthenium, iridium, osmium complexes. So they are actually they form lot of complexes, and some medicinal applications of these kind of metal ions, particularly photochemotherapy. They utilize this kind of metal ions. But a problem I just describe it and tell it afterward. And then I divided it into faster transition metal complexes like copper, oxyvanadium, cobalt, manganese, and iron complexes. So these type of metal complexes already have been developed and they have emerged as a very good photochemotherapeutic agent. Okay, so these are the example of heavy transition metal ions. So you can see it here. If we excite it, then the azide is removed. Okay, then platinum to actually the cisplatin product is formed, and then they are actually cross-linking the DNA, and these nitrogens kind of radicals, they are also killing the cancer cells. So these are different one kind of example. These are the example where they can generate a singlet oxygen, they can generate a singlet oxygen, they can generate a singlet oxygen. Okay, but the limitation that I wanted to show the heavy metal toxicity, because these are not the part of the essential metal ions, biologically essential metal ions, and because of the heavy metal toxicity and high energy visible light absorption, so they are mostly absorbed below the 500 nanometer. Still we are not able to reach the 600 nanometer goal. Okay, for phototherapeutic applications, these metals are promising but not enough for phototherapeutic applications. Now these faster transition metal ions, these complex, when they are formed, it is found out they can absorb at 600 nanometer. Okay, and holy grail is there. So if you have a 600 nanometer light with this kind of, then you can replace these porphyrins with these metal complexes, and you have the phototherapeutic application with this kind. Okay, so now this is up to this much. So we have done a lot of work in this, and other people like Professor Chakraborty, then Peter J. Sadler, and then other eminent scientists, they are working in this area. So we also have a contributed a little bit in that, and we are able to show some of the red light induced photochemotherapeutic activity with the metal complexes. Okay, but still there are some problems with these metal ions, with the metal complexes. Okay, what are the problem? The problems are like a solubility and delivery. This is the problem. Okay, metal complexes are less stable sometimes, and it is not sufficient to be we studied it some biological studies, but may not be, is not enough. Okay, and then absorbance, we have achieved is 600 nanometer. Okay, but still if it is a more and more lower wavelength side, it can absorb, so higher side absorb, then it will be more good thing. So it will be good for us to have. So then we have some plan. Okay, so just to use the nanoparticles. But why we have considered the nanoparticles? And I think you have a lot of discussions on the nanoparticles. So what are the nanoparticles? So I am not going to discuss about these things. So, and then just to have a comparison, this slide is shown here. So what are those nanoparticles? Okay, so these are the very small few atoms. Okay, so they have some different properties from the bulk. Okay, so various kinds of nanoparticles are there. Okay, so one dimension, two dimension, three dimension, they have a some spherical shapes, tubular, some very irregular shape. So these have different properties. Okay, different optical properties, different properties, so they can have a different applications, utilities. But why we want to introduce our nanoparticle to our studies? So this is a very mechanically very strong, thermally stable. They have shown excellent catalytic activities. Then electrical conductivity is also very good for that. They have excellent magnetic properties, optical properties. So these nanoparticles, gold, suppose for example gold nanoparticles are absorbing around 520 nanometers, so they can absorb in the visible light. Okay, so that is our purpose. And facial functionalization scope, so if you thiols, amines or acids something, they can, you can functionalize with the gold nanoparticles, so that scope is there. And of course this is very important, that it is, some studies have shown that nanoparticles are, if we attach to some drugs, so they can it deliver those drugs very efficiently into the target site, and they have some targeting property. Cancer cells can take up up to some 10 to 100 nanometer, sorry, around 15 to 20 nanometer particle. If it is less than that, so they can reflux it. And more than 100 nanoparticle, they cannot take it up. Okay, So they have targeting cancer cell targeting properties, and they can be retained in the cancer cells for longer time. So these actually properties prompted us to design metal based some gold nanoparticle metal complexes functionalized with the gold nanoparticles. Okay, so a lot of nanoparticles are used for cancer therapy and drugs, so I'm not going to discuss about that. What but why we have but what
Kulkarni,
excuse me.
please mute your. Okay.
Okay, thank you. Okay, fine. So our research interest, it is grows from here. So how the functionalization of photoactivable transition metal complexes into gold nanoparticles affect the photophysical and photochemical properties of transition metal complex or the gold nanoparticle, vice versa. Okay, so that is more interested. We are more interested in that. And then anti-cancer applications of these photoactivable transition metal complexes and functionalized nanocomposites. So we have started our work journey from here. So earlier we have synthesized these kind of iron complexes not attached to gold nanoparticles, and they have ability to hydroxylradical generations on LMCT excitations. These complexes, they have metal ligand to metal charge transfer transitions, and these transformer transitions at around 520 to 550 nanometer light, so they can able to generate hydroxyl radical, and this hydroxyl radical is produced from photodecarboxylation of this moiety. If it is attached to this type of group or attached to iron 3, then they can undergo photodecarboxylation, and it is iron once iron 2 is produced, then iron 2 produced immediately it's react with the molecular oxygen to generate the hydroxyl radical through the Fenton chemistry. It is called a photofenton chemistry basically, and Fenton type of reactions. And sometimes here also phenolate bond, if it is excite with the ligand to metal charge transfer transitions, so there is oxidation is going on. Okay, iron 3 become iron 2 and it become phenol radical. When it become iron 2, immediately it react with the molecular oxygen to generate the hydroxyl radical. So this chemistry, it is earlier it was established, and we have utilized this chemistry for anti-cancer applications. And these type of complexes, they have shown promising anti-cancer applications, but not in the red light but in the visible light. This is not our target actually. We have achieved some higher wavelength based photochemotherapeutic applications, but still we need to go far. Okay, now I have shown this. These are the metal complexes. People have prepared this type of material, CO releasing molecule. When you excite these manganese CO complexes, CO is released, and CO in activated states, it is thus killing the cancer cells. Okay, CO is to some extent, that is very good, but if you locally can generate the CO in more concentration, then it can be a uh, have a anti-cancer applications. Okay, so people have done the anti-cancer applications, so activating this molecule to release the CO. Okay, but it is only with the higher energy light, so this molecule doesn't absorb more than a 500 nanometers, so you have a limitation on that. They are showing some photoactivity but not in the higher wavelength side. These molecule, for example, it is there, these molecules are also singlet oxygen generating molecules on the photoactivated, but still only in a higher energy. So that is not our objective. Okay, but we have to see something else so that uh, they can have something a photoactivity in a red light. So in we have synthesized iron 3 manganese 1 lanthanum 3 complexes. Okay, and then nano hybrid, and we studied their we have the synthesize and characterize it, and photophysical studies we have done, solubility stability study. These are those studies are very essential for photochemotherapeutic applications. And then some we have done some TNT DFT calculations, And then we have shown cellular uptake, whether these molecules are going to the cells or not, and then photocytotoxic applications, then some ROS generations, okay, and then studies on cellular mechanism, okay, so cell death, mechanism of the cell death. So then we can, with these things we can conclude, so whether we need to develop that photoactivable transition metal complex functional gold nanoparticles for photochemotherapy applications, or we have to go in different pathway. Okay, so for example, we have synthesized, let's say this, only this manganese carbonyl, okay, and then appended to the functionalist in gold nanoparticle. Then we have prepared this iron 3 complex and then appended in a gold nanoparticles. Then similarly we prepared this lanthanum complex and it is appended in a gold nanoparticles. So we just compare these studies and then we'll see. Okay, so this actually first is that iron 3 complex has a gold nanocomposite as a strategic tool for targeted photochemotherapy in red light. So that paper is already published. So we are going to show you the result. So this is a synthetic procedure, okay, very simple way. So not involved any multi-step synthesis or very hard synthesis. We are able to get this compound, okay, and the complex itself it is showing the 573 nanometer. Okay, and your gold nanocomposite you have some band at 528, you already know. Okay, when you just attach to the gold nanoparticle we have another band at 660 nanometer. So there you can see the remarkable rate shift. 520, now 660, 573 it is not in the PDT window, now 660 absorption, now it is in PDT window. So we can excite, we can use this molecule to excite at a 660 nanometer to achieve our target photochem applications. And then IR characterization, mass characterizations, all this, then some material characterizations, it is already done. Then we have find it satisfied with this characterizations and synthesis, and then we find it out this hybrid nanoparticle. It is average sizes from 10 22 nanometer, and then DLS size is 142. It is hydrated, and average zeta potential it is somehow it is reduced because of the functionalization. And now we have done the theory. So so in this theory we have shown, we have prepared a gold nanoparticle of 1 nanometer, okay, and these nanoparticles homo to lumo electronic transitions it is occurring in 5352 nanometer, okay, and if you increase the size it accordingly. You know the these 20 nanometer nanoparticles they are absorbing at around 520 nanometer. So there is various size dependent studies are already done, okay, for the nanoparticles. Now what we have shown here, the electronic transitions that is happening in case of our um, metal complex functionalized gold nanocomposites. So we have just attached one of the such unit, and then we have seen that at 573 nanometer, okay, that is exactly we have got, theoretically it is also matching. So this is the electronic transitions from homo to lumo plus 1. That is the transition actually we are matching, okay. So that itself is showing some kind of sorry, 573 it should be 660 nanometer. So it is very close to that, and we can say that okay, so there is earlier it was a only gold nanoparticle 352, so now it is a 570 a kind of rate shift. So rate shift is natural phenomenon. So in this case if we attached a positively charged complex with the gold nano particle surface of the gold nanoparticles, and this is the potential energy surface, you can see this is the positively charged complex and gold complex is negatively charged, and there is electronic transitions from here to here, and that lead to electronic transition at a rate shifted electronic transition at 660 nanometer. So that is theoretically it is established, and also we have seen that is in experimentally. So after that, we wanted to have we have prepared one red light photoreactor, okay, from ourselves. Then we have studied in a red light induced some activities, okay, so like photo cleavage and the decarboxylation of this complex, and then this one, okay. So see here, So this is the your hydroxyl radical studies. Okay. No, sorry, this is a photodegradation of the complex. Okay. If you excite the complex with the light, then there will be decrease in that. Okay. So decrease in the absorbance. So there is something is going on. So it is not going back. So it is irreversible phenomenon. Okay. And IR band around 620, the carboxylate band, if you seen there, so it is actually with the light it is decreasing. Okay. With the exposure time it is decreasing. Okay. So then there is of course a something is going on, photodecarboxylation is going on. Okay. So similar thing we have seen in case of nanocomposites, metal complex with the gold nanoparticles. So it is decreased, bands are decreased, absorbance are decreased, and then your CO stretching is also decreased. So photodecarboxylation is clearly going on, and it is irreversible chemical reaction. So you are not getting it back. Okay. So singlet oxygen generation also we have studied, and we have seen that there are something these complexes are also able to generate the singlet oxygen, because iron 3 complex, it is not able to generate singlet oxygen, but it only generate hydroxyl radical. But gold nanoparticle has the property to generate the singlet oxygen when you excite with the light. But interestingly, it is shown that your nanocomposite is more active, okay, than singlet gold nanoparticle itself. Okay. So there is a synchronized phenomenon when you attach the metal, synchronized phenomenon. So when you excite these things, the red light, you have seen when nanocomposites are more efficient in generating the hydroxyl radical and then singlet oxygen in a red light than your metal complex alone or your gold nanoparticle itself alone. Okay. So hydroxyl radical generation also we have confront with the benzoic acid test. So there is benzoic acid. When a hydroxyl radical is generated in presence of benzoic acid, so it prepares salicylic acid. If you add some of the iron 3, then it will be able to generate that hydroxyl radical. Iron 3 hydroxyl radical will be attached with a attached to your benzoic acid from the salicylic acid. If we add iron 3 in that, so it can generate iron 3 salicylic acid, and it has an absorption at around this one. So it is slowly increasing. Okay. Okay. Now we have studied the photocytotoxicity, and we have seen that these complexes are actually photocytotoxic. So complex 1, it is in micromolar level, it is showing because it is able to generate the cytotoxic radicals. And in Hackard cells also, an A549, this is a lung cancer cell lines, and this is a skin cancer cell lines. So you can see it here, they can able to generate have a drastic differences in toxicities in red light. Okay. But this nanocomposite, if it is a greater than 500 microgram per ml, you can see it is a 56 microgram per ml in red light, and it is Hackard cells is more than 500, and here it is 72. So IC50 value means like at a concentration at which your cytotoxicity, your number of live cells will be 50%. So this is the phenomenon. So more is the less is the this IC50 value means more is the toxic. So you can see. But when we studied these things in WA38 cell lines, which is a normal cancer cell lines than these things, then we have able to see some toxicity is there, but it is a much less compared to what is there in the cancer cells. So two things we have achieved here. One, dark toxicity, it is our able to establish the nanocomposites are more cytotoxic. Okay. And if we just concentrate, we are able to convert in the molar concentration, it is a 6 nanomolar basically. So it is a very, very less. Okay. We are able to get a more efficient cytotoxic nanocomposite, number one, and it is also targeting a cancer cells. It is not going to the normal cell to that extent. Okay. So targeting plus cytotoxic efficacy we have achieved in this case of nanocomposites. Then we have studied the uptake. Okay. So by this facts, more is the shift here, so more will be uptake. So you can see this is the cell alone, this is a cell plus one, and this is the, you can see it here, the gold nanoparticle. It is gold nanoparticle uptake. I previously established that gold nanoparticles are delivered more better way. It take the drug the more better way to the cancer cells, and it is found true. And this is the confocal microscopy. You can see it here. Our nanocomposites were red fluorescence. Okay, you can see it here, and that is the DAPI, that is the nucleus staining dye, and this is the mitochondrial. This is targeting mitochondria. If we merge all these things, so you can see, okay, you can see it here in a bright field image, it is more visible. So our complex is actually going um, towards a it is actually going towards your nucleus, partially nucleus and partially to the cytoplasm also. So it can be a mitochondria and other places. So it is going inside. So this DCFD assay is done for to characterize whether complex in cells itself can able to produce ROS or not. So this is the study. More is the red shift here, more is the shift of the fluorescence band, more is the ROS generation capacity. Okay. So here you can see the gold nanoparticle, it is producing more and more ROS when exposed to the light. Okay. So this annexin assay, it is showing that some kind of apoptosis it is going on. So this is case of the gold nanoparticle here. So here you can see 19 plus 1%. So these are the number of cells actually. These are the cells. Okay. So in this quadrant means, this two quadrant means the apoptotic cell death. This is like a necrotic cell death. Okay. When you expose to the light, you can see it here. This is in dark, this is in light. Okay. So this has increased, and necrotic cell death is also increased. Okay. But similarly, similar thing is observed in case of complex itself, only complex also, because complex is also active, but we have observed more activity in case of nanoconjugates. And caspase, one kind of protein that is actually lead to apoptosis. So we have just studied the inhibition of the caspase, and we observed that this complex is able to inhibit the caspase. Okay, whenever there is a something ROS related cytotoxicity is involved in the complex, okay, so there will be actually caspase will be activated. Okay, caspase is one of the apoptotic protein. Okay, so these caspases in presence of our complex, when exposed to the light, we have observed the diminished effect of the caspases, and we are able to establish that caspase pathways actually it is um, involved in case of apoptosis. Then mitochondria membrane potential also we have developed. So there is, we have observed in case of this they are targeting the mitochondria actually, and mitochondria membrane that is disrupted. Okay, so this is the whole phenomenon. Actually, it is depend on if it is a complex is able to generate the ROS in presence of light, then it will trigger a mitochondrial membrane to be break down. Okay, mitochondrial membrane is breaking down, then there will be release of cytochrome C, and this will trigger a signal that will lead to a activation of the caspase, and this caspase ultimately lead to a BCL2 or Bax protein, these things pathways, and then finally apoptosis is formed, and then cancer cell undergo apoptosis, means cells suicide, cell is getting suicidal itself. It's a program cell death. So you are programming to cell for the cell death. So if you're killing the cells, that is a more and more inflammation will be there. So that is unwanted, and it will damage the surrounding normal cells also. But if apoptosis is always happening in the program cell, then there will be a non-inflammatory sites. It is not inflammation. So it is normally gone, and if it is cell is died, apoptosis, it is breaking it down. Then we have phagocytosis. With the process of phagocytosis, they can eat up and then throw it out, okay, from our body. So this is the thing. The conclusion is that when we attach to a gold nanoparticle metal complex, iron 3 complex with the gold nanoparticles, then there will be a red shift, okay, and that red shift can be utilized for
Hello. Is it Lingfeld?
that can become a better proxy model. Okay.
Your voice is not coming.
Uh, yes, better for cytotoxic model. Okay.
Please speak.
Yes.
Hello.
Hello. I'm not audible.
Dr. Mithun,
Yeah. Hello.
your voice
Yes.
is not coming.
Hello. Hello. Now it is coming. No.
Yes, sir, it is coming,
Yeah.
sir.
It's
Okay.
coming.
Fine. 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 Oh. Okay. Fine. Thank you. Thank you. So what I mean to say, when you functionalize your metal complex that is not very much suitable for phototherapeutic application, not ideal for photochem applications. Now, if you attach this gold nanoparticle with a complex with the gold nanoparticle, then it become a better model for photocytotoxic applications. Okay. So now what we are planning to do it, so whether we can co-functionalize your and our folic acid or not, because folic acid is actually targeting the breast cancer cell, and so we are actually able to achieve with the same metal complex with gold nanocomposite with the attachment of folic acid, so it will be targeting basically a breast cancer cell lines and shows a better efficacy. Okay, so in this way we want to proceed it, and we have not get any cellular data, but we have synthesized this compound, and in future we'll want to see what is the effect on that targeted photochemotherapy. Okay, so now I just wanted to show you the another example. So this molecule actually, sorry, this molecule actually it is showing this molecule is able to release the carbon monoxide when it photoactivated, but it is not done in the around 400 nanometer, you can see. But if you attach a gold nanoparticle, that you can achieve it in more than 600 nanometer. Okay, so in this region there is a something, there is a one peak is there. Okay, so this way there is also redshift. Okay, and we have utilized this redshifted gold nano composites and manganese 1 complexes for photochemotherapeutic applications. Okay, so these are the basically a characterization, so I'm not going to discuss on detail on that. So these photo release, these UV studies, they're showing some photo release. Okay, and this is a myoglobin assay in presence of if CO is released, then myoglobin actually it captured the carbon monoxide, and then some UV pattern is shown. So we have seen that kind of pattern. So we can confirm that with the photo activation, it releases CO, carbon monoxide, and this carbon monoxide is very very toxic. And rate law you have determined, and it is shown that this gold nanocomposite is much more faster in releasing CO than your normal complex counterpart. Okay, but here it is again, it is coming, it is the synergic effect of gold nanoparticle and the metal complex to have a more means faster rate of CO release, and that is very important. Okay, so other CO release is studied by the IR, that CO stretching frequency is decreased a lot when you excite with the light, and with the TGA also we are able to see the loss of the carbon monoxide, and from with thermally also it is possible. Okay, CO is lost. So we try to do some DFT calculation, what is how the CO is releasing. Then in this complex we are able to see when is photoactivated state, it is a triplet excited state, we have seen there is a lengthening of the metal carbon bond. Okay, in all the cases. Okay, and the lengthening of the metal carbon bond, that means it is destabilized. Okay, so it is going out. So after proving this theoretically, so then we studied the photophysical studies. So since gold nanoparticle is there, obviously it will show some synthetic oxygen generation, and it is, of course, it is more. So now actually we are able to make a dual photosensitizer. It is, it can generate the carbon monoxide also, it can generate the synthetic oxygen also. So both the toxic radicals have a synergic effect on the toxicity to the cancer cells. Okay, so these are the MTT assays, and we have seen that this in the light nanoconjugate is much more toxic, and this annexin assay it is showing that the some kind of apoptosis it is going on. Okay, and then cellular uptake is also gold nanoparticle, it is more. Okay, and interesting okay, so one of the ligand, that is, if I want to show you, okay, so this ligand actually it is become fluorescent, it is a fluorescent ligand, but when you attach to metal complex, that time it is not fluorescent. Okay, so we have utilized this phenomenon here. So with that exposure to the visible light, we have seen there is increase in fluorescence intensity. Okay, excitation is 350 nanometer, and this increase in fluorescence we have observed by FACS studies in the gold nanoparticles with the in the cancer cells itself. So when we, with respect to time, we just give the time, with time dependent studies is done, then we can see there is a shift in fluorescence band. That means more and more degradation of the compound is going on, more and more CO is released, and more this compound, this ligand is released, and ligand is fluorescent ligand, it is showing some fluorescence. And in the cells you can see it here, intensity is increased with respect to the time it is exposed to the red light. So with it, this is the time dependent studies. Okay, some it is 5 minute, 15 minute, and then 30 minute. You can see the deeply intense blue color. This blue color in the cells itself is due to the due to the release of the fluorescence ligand. So actually this is a theranostic. Theranostic means it can simultaneously, it can therapeutic effect is also there, and you can monitor this by fluorescence also. Okay, so diagnostic and therapeutic effect in a single platform, in a that manganese complex, manganese yoke functionalized gold nanoparticle it is having. So we have observed a similar thing, redshift on functionalization of the gold nanoparticles, and in addition with the CO release, it is a more and more cytotoxic, and it also generates synthetic oxygen, and it is actually theranostic. So with the exposure time, photo exposure time, it CO is released, your ligand is released, compound is breaking it down, and then it is become more and more fluorescent. Okay, and that is shown in vitro. So actually recently we have done another studies that is published in Inorganic Chemistry Frontiers. So it is also in the content page also, it can shown here itself that in IC50 value it is a 24 microgram in red light. Okay, but in dark it is greater than 500 microgram per ml. So there is a remarkable effect. Okay, and it is all the cells are dying by apoptosis. So what is the salient feature? Purity window 750 nanometers. So it is a very ideal photosensitizer. If you take the normal lanthanum compounds, normal without gold nanoparticle, it is showing around 450 nanometer absorption. So that 450 nanometer 300 nanometer rate shift is there. That is remarkable. And these lanthanum compounds, it is the first time it is shown here that lanthanum compound can also be used. Just if you can tune with them some other part like a gold nanoparticle and others we have done. And salient feature is that very high synthetic oxygen quantum in red light, remarkable relative to targeted PDT, and it's targeting the actually mitochondria and leads to oxidative stress, and it is a Caspase 3 dependent apoptosis. So all the qualities, almost all the qualities to be a ideal photosensitizer photochemotherapy application, it is achieved here with this kind of lanthanum complex. Okay, so in this study what we have done, this is the lanthanum complex, and we have functionalized in the gold nanoparticles, and then we have studied thoroughly this. So see here, this is the EV visible absorptions here. So this is the complex number 1. You can see it is no absorption at around these things 500 up to 500 nanometer. Gold nanoparticle, it is this one 520 nanometer, and if you complex, if you see it, this is the band is there around 751 nanometer. So this is the very remarkable observation in this study, and we have characterized these gold nanocomposites of the lanthanum complex in the bacterium, powder XRD, DLS. And then we done pyridine assay. Pyridine assay is the one kind of assay that it confirm whether in your molecule there is some triplet excited states or not. So if it is increasing, that intensity of the pyridine fluorescence intensity, if it is increasing with the exposing the gold nanocomposite with the light, that time it can be seen. That time it will be seen increase in the fluorescence. Okay. That means there is a presence of triplet excited. Then if it is triplet excited state, then if you can remember the Jablonski diagram, it is shown in the earlier cases. In Jablonski diagram it is shown. That time we have seen that if triplet excited state is there, so that it can able to generate the singlet oxygen. So in fact it is. So its singlet oxygen property, okay, singlet oxygen property, it is very high. Okay, so that plot itself is showing, and singlet oxygen, presence of singlet oxygen we have determined by the presence of by having the fluorescence at around this when you photo expose. So this is the band for singlet oxygen.
Doctor,
And so
how much PPT is there remains?
it is almost done.
So please conclude these things so that.
Okay, fine. Sorry for that. It is taking a longer time. So we have done the theoretical calculation on that. It is showing that how the curcumin actually they have presence of triplet excited state can be able to generate a singlet oxygen. Okay, and then confocal studies, it is showing the where this actually it is going. So it is targeting actually the mitochondria. And then cytotoxicity assay, you can see it here again. This is in dark greater than 500 nanometer, and here it is 25 microgram per ml. So same thing is happening in a normal cell. It is not there. Activity is not there. The cancer cell it is having. Again, apoptosis is there going on, and then there is a uh, mitochondrial membrane potential disruption, and then caspase activation is there, and then ROS is also generated in that. So ROS, when it is generated, so that time this is a very normal that it can disrupt the mitochondrial membrane, and then cytochrome C is released, caspase 3 pathway is activated, and then normal apoptosis is there. Okay, so this is the mitochondrial membrane potential determination. So sorry, this is the BAX and BCL2 protein expression studies. So it is shown that BAX is upregulated and BCL2 is downregulated. So that is basically a kind of caspase dependent pathways apoptosis. Okay. So summary and conclusion, just I want to say that when you append the manganese carbonyl with a gold nanoparticle, so in the red light region there is a red shift, and in this region you are able to generate a CO and then singlet oxygen and lead to a higher cytotoxic efficacy. Similar case it is in iron 3 cases also. So it has more cytotoxic efficacy than your normal iron 3 complex that your nanocomposite is having. Similarly, similar thing we have observed in case of lanthanum also. So that means ultimate conclusion is that if we attach the metal complex with a gold nanoparticle, then we will be able to have some kind of better photosensitizer, so that can have more better photocytotoxic efficacy. Okay, so that is the conclusion here. And I just want to acknowledge NIT Manipur and DST, CRB, BRNS, and ICMR for funding, and then Professor Chakraborty, Kaushar, Raja, Bhanita Ramu, and Dr. Amit Kunwar for collaboration. And I also would like to thank our director, Professor Gautam Sutradhar, Dr. David Singh, our registrar, Dr. Rajesh Bhushan from Dean Academic, and of course Department of Chemistry, and then my student Dulal Musib and Muinakpal for his remarkable work, okay, remarkable hard work. And of course, I just want to thank you, Dr. Bipu Prasad Swain, the coordinator of this FDP, for inviting me to give a presentation on this topic. Okay.
Thank
Thank
you,
you.
Dr. Mithun Roy,
Thank you.
for
Thank
your very, very exciting and informative talk. So what you say? Then questions. Because after question, I will take attendance. Please stay here. So attendance will just to verify these things. Before this, if you have any questions, then please ask to Dr.
Sure.
Mithun Roy.
Sir, should I ask a question?
Yeah,
Yeah,
please.
yes.
Myself, Dr. Pankaj Kumar Singh from IIT BHU.
Yes.
Yes, please.
Yes.
Your presentation was very nice. Actually,
Thank you.
I want to know how your study is different from the basic photosynthesis process.
Photosynthesis. Oh, yeah. So photosynthesis here, actually the light, you can, if you see the, remember the photosynthesis, manganese that cofactor. So actually it is a work as an antenna, okay, and it harvests the light and then activate the Z pathways, okay. So and then water splitting reactions is going on, in these things. So actually, but in this case, actually we are using the photosensitizer to activate the some like say for example your triplet oxygen, okay, to become a singlet oxygen. Then molecule itself, it is having the carbon monoxide that can be released, or it can be your that let's say iron complex. There is a, if your MLCT excitation is there, then can it able to undergo for photophantom type of chemistry. So actually we are here, our molecule is active, not active in the dark, but when you expose to the light, then it become active. So in the tumor cells, what you can see, the target specificity is very important. So if you take a chemotherapeutic drug, your systemic side effect is very much concerned. Okay, so it goes to the normal tissues also, and create a secondary malignancy. But this product system, that it can go to the normal cells also, but to some extent, but it will not harm anything. Okay, but only the thing is that the tissues where you can take the light into that, only those tissues will be affected. So photosynthesis is rather a same kind of chemical reactions. Okay, so by harvesting light, we are also almost not like that, not almost like that, but here we can harvest the light. Okay, use the light basically to activate our photosensitizer to lead some chemical reactions. So that is the differences that you can see.
Okay, thank you, sir.
Okay, thank you.
Any more questions? I think there is no more questions. So any
Okay.
question, then you can contact direct also. So
Yeah, sure.
now it is, we can conclude this talk, and thank you, Dr. Mithun Roy, for his talk. Thank you all for participants. So to now, I just take attendance to just verify, because I have already taken this attendance. So one by one, if you present, then please tell me you are present, so that I will put these things. B. Adhavan. Hello, present. Kuldeep Rathore Singh. Kuldeep Rathore Singh. Hey Priya. Hello. Nirmala Devi. Hello.
Yes, sir, you are audible, but I think the candidate is not present.
My voice is not coming.
Sir, your voice is coming.
Your voice is clear, sir.
Okay. So please, at least in last day, I should to identify who is present. Of course, I have marked present or absent, but to verify it. Otherwise, if your mark is absent, then you may not get certificates from AICT. So that's why I want to clarify this name, and please say at least present. Okay. Noyes Kumar. Hello, Noyes Kumar is present. Noyes Kumar, Sneha Leo, Sribhi Yadav. Hello, Sribhi Yadav. Yes, Binod. Sribhi Yadav. Okay. Neeraj Sharma. Nobody is responding. Then what to do?
Sir, the
What?
candidates might not be present, but your voice is audible to us.
Yes,
But that
yes.
candidate is not responding. That means that candidate is not present in the team.
Okay.
Sir, just we are told our name and you mark our attendance. So those who
Yeah,
are
that
listening,
will be much better, sir. I am Anita Gupta.
That's okay. But the thing is that there is a 200 plus registered.
Right, right.
I cannot identify all these things. It is because there is 3-4 pages. So every
Should we
pages.
write our name in the chat box, sir? What you suggest? If you suggest, we can write the name in the chat box with the email ID.
I think that will be better if you just rectify these things and send the name. Then I'll just verify it because already attendance is taken.
Right, right.
Okay, so
sir.
please,
So right now 107 are online. Though
online, but
there are
attendance
200 more
number of
registered.
faculty and a PhD students. Some few are PhD students. They are registered to around 200. So that's why this problem is arised. If the number is the same, then there is no problem. Okay. Anyway, please send to my. Otherwise, you just email me. Otherwise, will be better. My
Sir,
email is
I am Abdullah, sir. I am present.
no, no, the same. This one by one, I cannot do this thing. No, it is 200, and how can I identify? There is in AICT page. There is 10 pages. Is there attendance? Okay.
Sir, we will write our name and email ID.
Yes, yes. Yes, that is better.
Right, sir. Chat box, we are writing our name and email.
Okay, okay, okay. Thank you.
Okay, sir. Okay.
Thank you very much. Then another talk is around 2 o'clock, but we will start little late. Okay,
Okay,
2:15.
sir. Okay.
Okay, and this is the last one. After that, I will give this quiz that is total 30 questions. Okay.
Okay, sir.
Sir, are we starting now, sir? Hello.
ஆமாம் சார் ஆமாம் சார். சார் இன்னும் நிறைய இருக்கு. 5 வயசு இன்னும் ஆச்சுண்ணா. கிருஷ்ணன் சார் பஸ் அண்ணா சொல்றேன் சார். Sir, if I complete college fees, can I do courses, sir? Phone பேச போறோம். நல்ல பேசமன். How should I pay now, sir? எப்படா பே பண்ணுங்கிற என்கிட்ட கேட்டா
இன்டர்ன்ஷிப் ரெஜிஸ்ட்ரேஷன் பண்ணிட்டாங்களா
சார்
இன்டர்ன்ஷிப் பசங்க ஏசிடி இன்டர்ன்ஷிப் பசங்க ரெஜிஸ்ட்ரேஷன் பண்ணி
ஒருத்தனும் பண்ண மாட்டேங்கிறாங்க நேர்ல
இருக்காங்க பாருங்களா போஸ்ட் பண்ணுங்க
எப்ப போட்டாங்க
போட்டுக்காங்க
இன்னைக்கு இன்னைக்கா
இங்க எதுவுமே போட்டாங்க நம்ம சும்மா பார்வர்ட் பண்ணிட்டு இருக்கோம் இதுல பாருங்க லிஸ்ட் கேட்டு இருக்காங்க என்டர் பண்ணலாம் செகண்ட் இயர் மெண்டர்ஸ் என்டர் பண்ணிட்டு இருக்காங்க பாருங்க நிறைய பேர் பண்ணியிருக்காங்க
எப்ப அனுப்புனாங்க
மார்னிங்ல இருக்காங்க பாருங்க
இந்த டிசிஎஸ் போர்டு விட்டாதா
அது இல்ல இது ஏசிடி செகண்ட் ராஜா பசங்க வீட்டுல இருந்து 5 பேர் பண்ணியிருக்காங்க அப்புறம் ஆஞ்சலினா எங்களோட பையன் 5 பேர் பண்ணியிருக்கான் ஒரே மாதிரி கோர்ஸ் தான் பண்ணிருக்கேன்
சார்
செகண்ட் இயர் தான்
அதான் செகண்ட் ஆமா செகண்ட்
நம்ம பேர் எல்லாமே நம்ம பையன் ஒன்றும் பண்ணல
பசங்க என்டர் பண்ணுவோம் நம்ம என்டர் பண்ணுவோம்
நாம தான் என்ட்ரி பண்ணணும் குரூப்ல போஸ்ட் பண்ணனா போய்
எப்போ போட்டிருக்காங்க மெசேஜ் மேடம் எப்ப அனுப்பியிருக்காங்க
மேல போகிறது லிங்க்லாம் இருக்கும்
இதா
அப்படியே அனுப்பி குரூப்ல போட்டு நேம்லாம் வாங்கி போட்டு
மெசேஜுங்களா ஸ்மார்ட் இந்தியா ஹேக்கர் தானா
அது இல்லை கீழே கீழே ஏசிடி ஸ்பான்சர் ஏசிடி ஸ்பான்சர் இருக்குமே
மெசேஜ் எப்படி அனுப்புவீங்களா
ஏசிடி ஸ்பான்சர் போட்டாங்க இங்க இருக்குதா
மெசேஜ் எப்படி அனுப்புங்க ஒரு குரூப் தானா
வேற குரூப்ல போட்டாங்க ஒரு நிமிஷம் அஞ்சு இருக்குது அவங்க ஏதாவது ஒண்ணு பண்ண சொல்லுவாங்க எல்லாம் பண்ணிட்டு சர்டிபிகேட் வர முடியாது இங்கேயும் ஒண்ணுதான் போட்டிருக்காங்க ஒண்ணுதான் போட்டிருக்காங்க
பண்றாங்களா நல்ல இது என்னதான் போறதே இல்ல நேரத்தை விட்டு நேரம் இல்லாம இருக்கு
ஒரே பேட்ச் அடுத்த ஒருத்தர் வந்து இங்க சேர்ந்து
ஜெகன் பத்மநாபன்
பாத்தீங்கன்னா ஸ்பீக்கடா இருக்கு ஏன்னா போட்டு பாதிக்கே இருக்கு
வேலையே கேட்டு போ பேலன்ஸ் எல்லாம் கரெக்டாக இருக்கு தலைமறைவாகவே இருக்கு சரி ரிசர்வ் பண்றீங்க
யாரும் உட்காரக்கூடாது எல்லாம் பிரிஞ்சு உட்காருங்க அதுதான் கேட்குறேன்
ஆரம்பிச்சதால இவாங்கன்னு சரி இவாங்க
Right. Hello, everyone. Good afternoon, everyone.
Good afternoon, sir.
Good afternoon, sir.
So this is our last talk of this FDP development program. By our Dean of MIT Board, Professor Rajesh Kumar Bhushan. His expertise in actually he is from mechanical engineering, and his expertise in nanocomposite, biomaterials, and other etc. His recognition is much more. I just introduce as a faculty, as an administrator, and he is also several experience in other institute also, and he is recently he is a 2% scientist of in the world, top of the world. So I introduce its talk as entitled as a nanocomposite material and their applications. So actually, in this talk, I just say he's give the talk on the same name of me. So plus, just see it whether it is visible or not. Whether it is visible to everyone.
Yes, sir. Yes, sir.
Okay. So there is a very little introduction. Actually, I think it is not. I am not so qualified to introduce him. So maybe he's so good administrator and good person on behalf of you, and good colleague. As personally, I know for so far. So he in his talk he will give this title as Nanocomposite and their material. I hand over to him, and please enjoy this talk, last talk. And after this talk, I will take a quiz and ended this session. So thank you very much to everyone, and I will invite him personally.
So the topic for talk is nanocomposite materials and their applications. So brief idea about these things first I'll give. Then we'll go to some fabrication part and their applications. So first, what is nanotechnology? Now nanotechnology, we can see some for comparison, it is shown that nanotechnology that deals with material and particles in the nano size. 1 nano is 10 to the power 9 meter, and some for comparison dust mite 200 nanometer, 200 micrometer, sorry, then ant is 5 mm, then human hair 10 to 50 micron, then RBC is 2.5 microns, DNA 2 to 1 by half nanometer. Then we have cellulose nanofibers 200 to 900 nanometer. Then RBCs. So this is some idea about the nanometer and their comparison. You can compare it. Okay. Then further, nano size means at the atomic level. Now percentage area in proportion to the total volume is changed compared to the material in the bulk. Now uses are in cars, motors, aircraft, energy, electronic equipment, paints, cosmetics, medicine, and packaging. Now different definition for nano. You have nano clusters. That is the collection of units, atoms or reactive molecules of about 50 units. Then nanocellular colloids, a stable liquid phase containing particles, and particle is 1 to 1000 nanometer size. Then nanoparticles is 1 to 100 nanometer is range. That could be non-recrystalline, an aggregate of crystalline, or a single crystalline. Then you have nanocrystals, a solid particle that is single crystal in the nanometer range. So this was the different definitions of nano. Now, nanotech invention, nano is not new. For example, nanowires of silicon and other material have remarkable optical, electronic, and magnetic properties. Even in the 19th centuries, nanoparticles soot in the tires were used to make them black. Then nano bits of gold and silver have been added to color pigments in stained glass in 10th century. Color depends on the size of the particles. So then you can also have a feel of nano size in the sugar molecules. Then milk and humans are living proof of nanotechnology. Now, why nanoparticles are different from the bulk material? So nanoparticles are different from the bulk material and isolated molecules because of their unique physical and chemical properties. So what are those properties? First is catalytic. So example are better catalytic efficiency through higher surface contact. Then electrically you have increased electrical conductivity in ceramics. Then magnetic, increased magnetic porosity up to certain critical size. Then super paramagnetic behavior, mechanical improve hardness and toughness of metal and alloy, ductility and superplasticity of ceramics. Then optically you have spectral shift of optical absorption and fluorescence properties, increased quantum efficiency of semiconductor crystals. Then spherical, increased selectivity, hollow sphere for specific dryness, transportation and control release. Then biological, you have increased permeability through biological, that is the various membrane, blood, brains, barrier, etc., and improve biological probability. So these are some properties and they are examples of nanoparticles. Now, nanotechnology is basically an interdisciplinary field. So it has interest in physics, medicine, engineering, biology, and chemistry. Now there are two basic approaches for formation of nanomaterials. First approach is the bottom-up approach. So this is also called organic synthesis and self-assembly. So size is shown, you can see up to your 10 nanometer to 100 nanometer. So at the 100 nanometer, you have biomolecules and nanoclusters. Then second approach is top-down approach. So in the top-down approach, you have two approaches, photolithography and micro contact. And currently gap exists in the engineering of small scale devices, whereas conventional top-down processes hardly allow production of a structure smaller than 200 to 100 nanometer. Limit of regular bottom-up approaches in the range of 2 to plus minus 5 nanometer. So this is an area still open for the research. So practically the nano devices can be made by using the different techniques. So somebody who is still interested in the nanomaterial nanotechnology, they can develop or they can improve a existing process of fabrication and go for it. Now nanoparticles are different types. First we have pure metal nanosolids, that is the silver, gold, copper, iron, nickel. Then bimetallic, so you have platinum, rhodium, platinum, nickel, cobalt, molybdenum. Then you have metallic oxide, titanium oxide, zinc oxide, ferrous oxide. Then you have metallic chalcogenides like PBS, CDS. Then you have ferromagnetic safe memory alloys. Then further you have conducting polymers, that is the metal nanoparticles, composite SSR. So these are the different category of the nanoparticles. Most of them are in use for the different industrial applications. Now, synthesis of the nanoparticles, how you can make them? Well, first is by chemical reduction, the reverse synthesis, solo gel process, aerogel process, microemulsion, co-precipitation, decomposition of organic metallic compound, hydrothermal lutes, solution evaporation process, then sonochemical ultrasonication, encapsulation in the host, and gamma ray irradiation in the presence of redox mediators. So these are some of the process for formation of nanoparticles. Now, what are the challenges in the nanotechnology? So for the fabrication and processing of nanomaterials and nanostructure, the following challenges are to be made. Overcome the huge surface energy. It results in the enormous surface area or large surface to volume ratio. So this is research challenge also. Then ensure all nanomaterials with desired size, uniform size distribution, morphology, crystallinity, chemical composition, microstructure, and altogether result in desired physical properties. So this is really a challenge. Although many processes are available, but still the correct morphology and crystallinity is difficult to obtain. So the people interested in this area, they can go for better morphology and crystallinity. Then prevent nanomaterial nanostructure from concerning through either postward ripening or agglomeration. So agglomeration is to be further avoided. This is also a research challenge. Now we come to, after nanotechnology, nanoparticles, we come to nanocomposite. Now nanocomposite are broad range of the material consisting of two or more component with at least one component having the dimension in the range of 1 to 100 nanometer. So suppose one component is having the dimension of 1 to 100 nanometer, then you can call them the nanocomposites. So it will have two or more component. The nanocomposite consists of two phases. So first is the nanocrystalline phase, that is mainly the nanomaterial. Then you have the matrix phase. So phase can be inorganic, organic, and organic. So these are the different combination of the phases. But nanocrystalline phase means basically the nanoparticles. The nanocomposite means nano-sized particles, that is the metal, semiconductor, dielectric material, etc. embedded in the different matrix material. So different matrix material can be ceramics, glass, and polymers. So this is how the nanocomposite is formed and they are identified. Am I audible to all?
Yes, sir. Continue, sir.
Yes, sir. Yes, sir.
Okay. Thank you. So then we have general features of nanocomposite. So nanocomposite differ from the traditional composite in the smaller size of particles in the matrix material. So basically, if you define a normal composite with the nanocomposite, the nanocomposite means mainly the nanoparticles. Size, small size may cause physical sensitivity of bulk material to physical or mechanical energy. Then higher chemical resistivity of grain boundary. So physical sensitivity is like small size effect, then quantum confinement effect. Chemical resistivity is the higher gas absorption, increased nanostochasticity, degrowth, rotation and orientation, subgraining and assembly. So these falls under chemical reactivity. Now you have physical sensitivity. Under physical sensitivity, small size effect. So that is when the particle size in the composite material approximately length of physical interaction with the energy such as wave, electromagnetic wave, periodic boundary conditions of coupling interaction with the energy, behave different from of its microscopic counterpart, which result in the unusual properties. So the main point over here is that if you consider the particles at the different level, first the macroscopic, that means more than micron size. Second is microscopic, that is the micron size 10 to the power minus 6 meter. And third is the nano size particles. So if the size of the particle is different, then that will affect the properties. Even the material is same. Suppose material is gold only. So if you say macro size particle of gold, micro size particle of gold, and nano size particle of the gold, so they will behave differently. That is the meaning here, small size effect. Then you have quantum confinement effect. So that is when electrons are confined to a small domain such as nanoparticles, the electrons behave like particles in a box, and their resulting new energy level are determined by quantum confinement level. These new energy levels give rise to the modification of optoelectronic properties such as blue shift light emitting diodes. So this is quantum confinement effect. Then you have chemical reactivity. So higher gas observation, that is the large specific area of nanoparticles can easily observe gases. Then increased non-stoichiometry of phases, that is the nanoparticle easily form chemically unsaturated bonds. Then regrowth, nanomaterials are probably easier to recrystallize and regrow in processing and service condition than the traditional material. The rotation and orientation, that is crystallographic rotation and orientation of nanoparticle have been found in the processing of nanocomposite. Then subgrain nanoparticles enveloped into the larger particle act as the dispersed pinholes to divide the large particle into the several parts. Then assembly, nanoparticles are easy to aggregate and assemble in the liquid or gaseous medium. So that is chemical reactivity. Now you come to nanocomposite materials. So this is latex part, layered silicate, then dispersed nanocomposite. So nanocomposite can be formed by blending the inorganic monocluster, polyins, clays, metal oxide, semiconductor with numerous organic polymers or organics, and organic metallic compound, biological molecules, enzymes, and shallow gel derived polymers. So that means number of combinations are possible. Then you have resulting nanocomposites. So in the resulting nanocomposite, for example, resulting nanocomposite may exhibit drastically different properties than the individual component. So this is one cup, so made of glass in Roman 400 AD. So this cup appears green in the reflected light and red in the transmitted light. So use of gold particles and the behavior is different under the different environment. So electrical, mechanical, electrochemical, catalytic, optical, structural and mechanical properties are affected by the size of the particles. Then classification of nanocomposites. So broadly there are three classifications. One is increase in strength, hardness, abrasion by refining the particle size, then enhanced ductility, touchiness, formability, superplasticity by the nanophase, then change electrical conduction and magnetic properties by increasing discontinuous grain boundary surface. So these are the properties of ceramic based nanocomposites. Then second category we are having the metallic based nanocomposites. So the use of nanoparticle improve the hardness, strength and superplasticity, lower the melting point, increase electrical resistivity due to increased disorder grain surfaces, then increased stability of non-equilibrium components, narrowing and solid solution, then improved magnetic properties such as supermagnetism, saturation magnetization, and magneto-qualitative properties. So that is the metallic based nanocomposite. And next we have polymer based nanocomposites. So in this property are electrical, optical, magnetic, catalytic properties arising from the inorganic material and enhance thermal and mechanical stability originating from the polymeric matrix. So these are the broad classification of nanocomposite 3: ceramic based, metallic based and polymer based. Now advantage and limitation of ceramic composites. So basically here we are comparing the method of formation of the ceramic nanocomposites. So for formation of the ceramic nanocomposite, there are three approaches. First approach is the powder process, second is the sol gel process, and third is the polymer precursor processes. Now certain advantages and limitations are mentioned here. For example, powder process advantage is simple. Limitation is low formation rate, agglomeration, poor phase dispersion, formation of secondary phase like this. So because basically this powder process is in use now. Research component over here is that whatever is limitation of the process, limitation of the powder process for formation of ceramic nanocomposite. So you can devise a better process so that the limitation of powder process is overcome. Then second, the sol gel process, you can see number of advantages are mentioned here. But one problem here is the greater shrinkage and amount of voids. So amount of shrinkage and voids can be overcome by improving the process. Somebody interested in this can go for research in this area. And advantage of sol gel processes are number of advantages. I'll mention few of them. Process is simple, low processing temperature, high chemical homogeneity, and mainly it is applicable for production of composite material with liquids or with viscous fluids that are derived from oxide. So this is specific application. Then you have polymer precursor processes. Advantage is the possibility of preparing finer particles, better reinforcement dispersions, and limitations are inhomogeneous phase segregated material due to agglomeration. So agglomeration is not a big problem. If you improve the process, go for some optimization of parameters, the process can be improved. Then advantage and limitation of processing method for metal-based nanocomposites. So suppose you want to make a nano composite on metal-based, then methods are spray pyrolysis, liquid infiltration, rapid solidification process, then RSP with ultrasonic, high energy ball milling, and chemical processes, that is a sol gel and colloids. Now first spray pyrolysis advantage, few I will mention. So advantage with the spray pyrolysis is that it is effective for preparation of the ultra fine spherical and homogeneous powders. And limitation is the high cost. Then liquid infiltration advantage, short contact time between the matrix and reinforcement, and limitation, use of high temperature sources needed because the metal is to be melted. Then you have rapid solidification, in short RSP. It is simple and effective, but limitation is only the metal to metal nano composite can be made. Okay. Then RSP with the ultrasonic, it has good distribution without agglomeration, even with the fine particles. So here you can see this ultrasonic. If you add the ultrasonic with the RSP process, the agglomeration problem can be resolved. So you have seen in the case of ceramic based nano composite, there were problem of agglomerations. So if you add the ultrasonic with a particular process, then problem of agglomeration of particle can be sorted out, and you can see RSP with ultrasonic is not having any limitation. So that is the way you can combine two processes to overcome the limitation of them. Then high energy ball milling. So in this we have homogeneous mixing and uniform distribution. Then chemical processes. So they are simple, low processing temperature, versatile. Limitation is the weak bonding, low wear resistance. So these are the limitations of chemical processes. Now third category is the polymer based nanocomposite processing methods. So polymer based methods are pre-polymer from the solution, in situ intercalative polymerization, melt intercalation, template synthesis, and salt gel processes. Now first pre-polymer from solution. Some of the advantages I'll mention, like synthesis of intercalated nanocomposite wire based on the polymer with low or even no polarity. Industrial use is a bit difficult with them. Secondly, in situ interactive polymerization. So this is easy procedure based on dispersion of fillers. And limitation is the difficult control polymerization. Then next is your melt intercalation. So advantage over here is you can use the polymers not suited for other processes. And limitation application is limited to polyfluorines. Okay. Then you have template synthesis. So advantage large scale production, easy procedure, and limitation limited application based mainly in water soluble polymers. And salt gel processes. So this is already explained for two previous cases. They are simple, low processing temperature, versatile, and you have greater synkinesis. So that was the basically formation. Now we will go to some of the actual applications. First we will go to so nano composite already defined. Now I'll speak about polymer matrix nano composites. So what are the advantages? Enhancement of the mechanical, optical, thermal, fire retardant, and gas transparent properties. Precise control of dispersed inclusion is necessary. Then, characteristics difference between the nanometer size and the traditional filler composites. So, ultra low percolation threshold, particle-particle correlation arising at the low concentration, large particle number densities, extensive interfacial area per volume of particles, short particle distance, and comparable length scale between the particle size. Now, polymers in the nanocomposite. So you can see here, these are the polymers used in the nanocomposite: nylon 6, nylon 66, then polymethylene, polyester, polyester and ABS, polypropylene, polyethylene, polyethylene oxide, then polymethyl malicrate, then polycarbonate, and polyvinyl chloride. So then the you can also use the epoxy. So epoxy are used as the matrix. So different epoxies are polyurethane, polyslomax, unsaturated polyester, polyamides. Then preparation method for polymer nanocomposite. So these are the first is intercalation. Intercalation basically monomer intercalation and polymerization. Then in situ method there are two steps: in situ filler formation, in situ polymerization. Third is molecular composite. So you have LCP polymer alloys. Then direct dispersion of ultra fine particles. So these are the preparation methods. So some of the benefits: efficient reinforcement with minimum loss of ductility and impact strength, heat stability, frame resistance, improved gas barrier properties, improved ablation resistance, reduced shrinkage and residual stresses, and altered electronic and optical properties. So these are the major applications. Engineering polymer modulus. Then you are in the packaging of gases, oxygen, carbon dioxide, water vapor, and retaining the clarity. So these are the major applications. Property and use of nylon 6 nanocomposites. So you see here, these are the nylon 6 application, this pipe, this pipe, this pipe, this pipe. These are the nylon 6 application. Mechanical properties are given here. Tensile strength, fractional strength, so specific gravity. This is comparison of nylon 6 nanocomposite in compared to standard nylons. So it is 5% non-clay, then 5% and 30% and 30% glass. You can see how much the improvement in the strength. This is unfilled means standard nylon, and this is with filling with the nano materials. So here it has gone to 23,000. Then lot of improvement in the flexible modulus also. So this you can see here. Then application of PET nanocomposite. So this is oxygen permeability. It is food tray for army. Then it is bottles, Honeywell. So these are the applications of PET nanocomposites. Then you have exterior door panel from PP nanocomposite. This is the PP based. Nanocomposite are in active development for auto parts like TPU exterior door panel. This is photo from Monotel, North America, and General Motors. So that was from General Motors, door panels of vehicles. Now, general polymer nanocomposite, what is there inside? Nanocomposite fabrication, you have polymers, then these are the nanoparticles, then you have functional properties. So mechanical properties, you have filler, layered silicate, electrical properties, semiconductor metals, then magnetic property, magnetic particles. Then further you have layered silicate based polymer nanocomposites. So if you make a layer of silicate, so dimensions are given here. This is 1 nanometer, this is 500 to 1000 nanometer, this is 300 to 5 nanometer. So this particular place they have shown enlarged view. Then you have how to fabricate them. So fabrication, you have like cations, organic phenolic group, thickness is 1 nanometer, length is 300 to 1000. Plus you add the polymers or monomers. So then process is direct polymer intercalation or compounding. Then polymerization after swelling in the monomer. It comes from here, this comes from here, put together. Then you have intercalated nanocomposite. Then you will also have exfoliated nanocomposites. So two category you can get over here. Then conjugate polymer nanocomposites. So in this we have metal, semiconductor nanoparticles, conjugated polymers. Now charge separation and transport. This is bulk state. This is confined geometry. And then you have confinement of polymer chains, change in interchange intersection, then change in intermolecular energy transfer. So these are the conjugate polymer nanocomposites. Now research of thermoplastic and clay nanocomposites. So thermoplastic and clay use polymer is polypropylene. Companies Toyota Center R&D labs, and synthesis method is melt intercalation. Second, nylon 6, then again Toyota. Synthesis method is the melt intercalation in situ polymerization. Then you have used polymer polymers. Company is the DuPont. Synthesis method is the solution intercalation. Then polyester, company is ICI Polymer Industrial Technology, and synthesis method is the melt intercalation. So these are already in use, and further research can be carried out in this area. Now, commercialization of polymer nanocomposite, company like first RTP, polymer is nylon, application area is your resin. Then second is Eastern Chemical, polymer nylon, application area multi-layer PET. Then third is Biswell Polyrene, polymer is TPO, application the car exterior cladding. Then you have EB Industries, polymer nylon, application is the timing belt cover. Then ICI polyester, polymer is polystyrene, and application the clean barrier film. So these are the specific area for the specific polymers and name of the company. Then you have PP clay nanocomposite by melt intercalation. So some steps are mentioned here. First is mix simultaneously, silicate layer. Then you have malic acids. Then second is the in melt intercalation. Then second step is this. You get PP exfoliated structure of PP nanocomposite, and finally you get it. So this is how you can make it by melt intercalation. Now next is the block polymer based nanocomposite material. So in this you are having type of BCD depending upon the dimensions. First is the 0-dimensional OD, 0D dot. Second is 1-dimensional 1D or tube, and 2-dimensional, that is the sheet. So synthesis approach is like particles are synthesized in situ with the fixed BCP matrix depending upon the reaction and diffusion kinetics of the growth crystals. The nanocomposite is fabricated by co-assembly of BCP and nanoparticle that is synthesized depending upon the equilibrium thermodynamics. So block copolymer based, that is the basically BCP. Then BCP based nanocomposite material. So further you can see nature of structure, dark, this is 1D, 1-dimensional, 3-dimensional, 2-dimensional, 3-dimensional. This is volume fraction, and this nano additives. So here particle has to fit into the space provided by the variable block domain. Compatibility of particles point symmetry group within the majority component of respective BCP, and these are the abbreviations used. Now second is nanoreactor scheme. What is nanoreactor scheme? Two octagonal pattern of metal particle in a BCP matrix infiltrating the hydrophilic domains of spherical copolymer with silver salt. So this is substrate then swelling, then reduction, further reduction. This is silver, and finally you get. So this is from this paper mentioned here. Second, reaction, diffusion, control, nucleation, and growth process. So you can see steps over here. This is metal precursor complex, then metalomer, that is a stable metallic fragment. Then you have got metal crystal. From the metal crystal, you are getting the polymer stabilized metal crystal. So this is schematic description of formation of metalomers and the nucleation, growth, and stabilization of cobalt oxide nanoparticles. So steps explained for cobalt oxide nanoparticles. Then Xe2 synthesis. So here gold nanoparticles diameter 3 to 5 nanometers are found segregated between the PS and PP domain. Then larger silica nanocrystals, that is the 21 nanometer, are mostly located at the center of PP domains, and a system consisting of the block polymer and two different nano size crystals is explained here in this figure, reference of this paper. So here control of the length. So length you can control by varying the aspect ratio. So that was the polymer nanocomposites. Now nanocomposite application in the food packaging. So expectations in the food, expectations of the food industry are improvement of the mechanical properties, improvement of barrier properties, active packaging, and biodegradability and intelligent functionality. So that is the expectations of food industry for packaging purpose. So nanomaterial for food packaging, it is listed over here. You have nanocomposite, then nano coating, surface biocides, then active packaging, intelligent packaging. So some I'll read over here. First, like nanocomposite, incorporating nanomaterial into the packaging to improve physical performance, durability, barrier properties, and biodegradability. Then active packaging. What is active packaging? Incorporating nanomaterial with antimicrobial and other properties with intentional release into the consequent effect onto the packaging foods. So the quality of packaged food does not deteriorate. And last one, in the intelligent packaging, incorporating nanosensors to monitor and report on the condition of food. So this is intelligent packaging, the use of nanocomposites in food packaging. So some comparative study, nanoparticles coated polyethylene film for food packaging, development of passive and active barrier coating, the nanocomposite packaging containing silver and zinc oxide to increase the shelf life of fresh orange juice, the nanocomposite based packaging on post-harvest quality of ethanol treated kiwi fruits during the cold storage, then cellular silver nanoparticles hybrid material to control spoilage related microflora in absorbent pads located in trays of fresh cut melon. So these are specific applications. So Giardino coated thin films, antimicrobial packaging films, they provide resistance strains. Then damage to microbial cell membrane is less. Specific application. So this is how it look like. It is taken from one paper mentioned here. So it is how it look like. Evolution of antibacterial action for plain SCP film. In figure A and figure B, the Giardino nanoparticles loaded with SCP film by John inhibition method. So in the tray it is put. So it will protect the quality of food. Then this is kinetics of bacterial growth for plain and Jadeno based. So it is compared here over the different period of time, like 0 to on the bottom you can see hours, 0 to 6 hours, 60 to 120 hours, finally 300 to 360 hours. You can see here the deterioration is less if you provide the Jadeno film. Then inorganic, organic polymers. So you are having multi-layer hybrid polymers. Then you have polymer plus organic oxide plus active oxygen layer. Then flexible, transparent, almost non-permeable, low cost in oxygen, water vapor, and flavor permeation. So these are the advantage of inorganic, organic polymers in food packaging. So this figure combination of passive barrier layers with an active oxygen barrier. So this is how actually it works. You have active barrier layer, then passive barrier layer, active barrier layers, hydrogen polymer based oxygen scavenger layer, then passive barrier layer, hybrid layer. So this is the combination of active layer and passive layer. So this is one graph, UV activation after 0 days, 1 days, 3 days. Then silver and zinc, NPS and LDP. So orange juice in LDP packaging, high surface to volume ratio of nanoparticles, evaluated in the dark and light, and performance after 7, 28, 50 days of storage under the 4 degrees centigrade. So this is how performance is monitored. You can see the 10 micrograph of antimicrobial nanocomposite LDP film. Now nano packaging for kiwi fruits. Ethylene treated kiwi fruits, cold storage up to 28 days. It's allowed if you use this. Then silver and TiO2 nanoparticles in polythene. So this is used. These particles are used in polythene. So it will be matrix and nanoparticles. If you combine them, you get the nanocomposites. Okay. So there were two broad applications. Now this is presentation from some of the latest research papers. So this is research of year 2021. Here basically I'll focus on what are the research opportunities available for the faculty members and students in the area of nanocomposites. Okay. So starting from here, all latest research and what are the scope and opportunities available for faculty members and the student. So this is multifunctional cell nanomaterial. Name of the paper and details are mentioned. So this is basically application of mesoporous silicas. Now this is showing scheme of methods, fabrication, grafting and co-condensation. So this is grafting approach, then co-condensation approach. This is used. Now location of functional group and other groups on the surface. This you have mesopore surface, then external surface. So figure A is location of nanoparticles into the wall of silica. Figure B onto the external surface area. And figure C is the encapsulation in the silica cell. Now these are examples of various inorganic nanoparticle applications. So their application in the chemical industry, environmental protection, electronics and IT, energy and automotive industry. So here in the center you are having the inorganic nanoparticles, and biomedical applications are in the imaging, Then therapies, biosensors. Okay. Now these are the representative nanomaterials as nanosensors for various pathogen detection. So it is mentioned here some of the material. First, some of the materials I will mention here. So first is the nanomaterial lectin functionalized and isotropic AGNPS sensing strategy in the SPR, that is the optical sensor. Then second is bioconjugated magnetic beads and fluorescent polymers sensing strategy fluorescence, that is optical sensors. Then carbon dot ZNO nanorods. So electrochemical, that is electrical sensors. Then one more ZENV modified magnetics, that is the magnetic relaxation magnetic sensor. So these are latest nanomaterials for using sensors, and details are mentioned here. So further, if you want, you can see from the paper. Now, the primary application and potential properties of the hybrid coating. So coating is again made from the nanomaterials. Hybrid coating, resistance, sensors. If you use the resistance properties, then you can go for the anti-corrosion, improved mechanical properties, self-healing. In the case of sensors, for gas detection, fire detection, glucose sensing, then biomedicine, improved cell adhesion, improved cell differentiation, antibacterial effect in the food safety, UV blocking, antioxidant releasing, then agnotate freshness. So based on this paper is of year 2021. So as a teacher, we have to be in the research also. The point over here is what research scopes are available in the area of nanocomposite. So research scopes, nanomaterials are also beneficial in overcoming some environmental issues such as quality of water and air as well as the waste recycling. Now improvement in the quality of water, if you can develop a good technology, means or a better technology than the one which is available, because good quality of water is a major problem in mainly in the metros. So quality of water is deteriorating. If you can use the nanomaterial nanotechnology for this water and air, main problem in the cities. Then waste recycling, again major problem in the city. So these are the three areas which opens lot of scope for research as well as the business also. I have read also and listened also, people are making lot of money in the waste recycling business because they have developed some systems and technology, they are able to use it. For example, nano-based multifunctional sensors, that is the chemical, optical, electrical, can selectively trace the amount of toxic compounds. Next is nano-based absorbents may help to capture these pollutants from the environment. Depending on the surface functionalization procedure, nanoparticles shows completely different properties and can be used as a base to obtain a range of new smart material that can contribute to mitigate the mentioned global issues. So one more research area, development of the new smart materials. New smart means the which is already existing better than that. So if you can do that, a good area for research. So that was a year paper of year 21. Now one more year. So these are the natural fibers finding a lot of use. So you can see figure A, needle punched, non-woven. Figure B, you are having 100% wool. Then C and D figures that the seaming is there. Seam means some stitching has been done in the figure C and figure D. So paper from the year 2020, details are mentioned. Now, preparation of sample for laboratory test. This is grassroots system that formed on needle punched, non-woven. So now you can see the different steps. You can see the different steps for formation. So these are the physical and mechanical parameters of non-woven used in WAGs before and after biodegradation process. So then we are having now what is the real requirement here? Increased water retention capacity and gradual release of nutrients to soil, natural fibers. So this is one of the requirements. Then natural fiber based root system. So this is one of the papers showing one application, but as we are aware, there are a lot of natural fibers in our country, in our surroundings. So you have to just identify the proper fiber which will be suitable for some application, industrial application or biomedical application. You can go for research in that area. Then next is self-assembly smart material for biomaterial applications. Now you see here lot of bio applications of nanocomposites. So starting with monomer and polymers, carbon nanostructure, metal nanoparticles, inorganic nanoparticles, biomolecules, then molecular interaction. So under this external stimuli, internal interactions, then self-assembled structures, then finally the biomedical applications in the biosensors, drug delivery, bioimaging, 3D cell culture, nanofabrication, gas, and other. So see, for some material, if it is to be used on the body or inside the body, the basic requirement is the compatibility. So the material which we are eating in the form of food, that means that is biocompatible with our body. And some of the natural material which our body is able to sustain. If you can make a device based on those material, then it will be a real application of nanocomposites. So a lot of scope for research. Now this some summary: nano biometallic structures, nanoparticles, nanoneedles, nanorods, nanoflowers. The material used for them are gold, silver, palladium, platinum, silicons, silicon oxide, an application in the drug delivery, tumor targeting, then wound and burn care, implants, lot of materials, research is going on, then bone replacement, implant coating, huge area for research of the nanoparticles, nanomaterials, nanocomposite in the health sector. Nanotubes, you are having carbon application in the drug delivery, bone regeneration. Then third structure is the fluorines, nanocells. Materials are carbon polymers, glycolic acid, application drug and gene delivery. Then you have nanomaterial. Next is the semiconductor quantum dots, layered or flexible. Materials are carbon, zinc oxide, titanium oxide, polytic, then titanium, polyurethane, and application the composite skin graft, chronic wounds, burn wound, skin diseases, customized fat graft, Okay, then nanofibers application in the wound care and wound world. So, lot of applications. So then main covalent interaction useful in the cell assembly. So this is electrostatic, hydrogen bonding, hydrophobic, pi-pi interaction. So these are some of the useful polymetric, supermolecular structure, hydrogel, polymeric, then dendrimic, liquid crystals, layered biopolymers. Okay. So now future directions in this area, what are future directions? Self-assembly properties, mechanism and application in different smart biomaterials point out numerous advantages and is being main reason for drastically development in biomedical and other related fields. See, one more point here I would like to make that not only the PhD, but if you want to get a research project, so research project either by the government or by industrial houses is provided only in the field in which there is an economic output. Economic output means if your research will be converted into some application, useful industrial application. So whenever you select a field for research, it is better see whether that particular research or project or technology will be in use at least for 10 to 15 years. So you can also drive economic benefit from them. Now many research groups in the worldwide are working on small materials, small biomolecules to develop the novel material biomaterials and explore in biomedical engineering, pharmaceuticals, environmental science, agriculture, analytical science, material science, and energy science. Green energy is coming in a lot of way. So the requirement of the green energy is basically generation of the energy, electricity, plus protecting the environment also. So if you can develop some technology, use biomaterials or nanocomposite or nanoparticles to protect the environment as well as generate the electric energy, that will be a good area for research. So I'll stop here only. Any question from participant sides?
Good afternoon, sir.
Good afternoon.
Sir, my name is Abdullah. I am having one, two questions.
Yes.
Sir, if I am making a particulate filled polymer composite,
Yes.
how much filler should I add at max to form a composite?
See, for answering this now, there are two approaches. One approach is that first year to study the physical properties of both the materials, number one. Okay. Number two is there are certain approaches in the micromechanics of the composite material.
Okay.
So by using those approaches and calculations, you can find out what can be the maximum percentage of the particles which you can put in the matrix. And third is after you get the numerical result, you can also use some softwares to cross-check those numerical results.
Sir, if it is percentage by weight, how much can we go? Or if it is a percentage by volume?
See, percentage by weight based on the papers or such which I have seen so far. So that is around 30%. 30%, but it varies from again matrix and the particles. But maximum 30% based on the papers which I have seen.
Sir, one more, sir.
Yes.
Actually, I'm working on low density materials. What
Okay.
happened, sir? I have prepared one particulate filler. So
Okay.
while preparing that filler, I prepared that particulate in the grinder, and
Okay.
it liberated more heat, and 2 grinder blades were gone. So
Okay.
and if we actually I have added that one in the polyester. So
Okay.
my point is that if I am taking 3 percentage by weight filler and
Okay.
97 percentage by weight polymer, that is okay, sir. If I am
Okay.
increasing the percent beyond 3, if I am taking 5 percentage by weight filler, so non-uniform mixing agglomeration is forming, sir.
So see, that's why I told na. For that na, what you can do is what problem you told blades have melted or broken down.
Broken, sir. Broken, sir.
Broken, so it was because of some mechanical failure or heat.
Maybe, sir, due to heat, sir, because that material given more heat, sir, that liberated more heat.
See, you can do 2 things here. First thing is that you can select the blade material of the some better materials. So the blade material which you used was which material?
Sir,
Blade which you have used now, what was the material?
that is Usha grinder, sir.
Usa grinder, okay.
Yes, sir. Yes,
So
sir.
now for that now you have to take some special grade of stainless steel, then you have to make the blade separately.
Sir, sir, sir.
That is one point.
Sir.
Second point, for agglomeration now, what you can do is you can use the ultrasonic system along with that while fabricating.
Sir, ultrasonic this one
Assisted.
mixer, na, sir.
Means nahi, mixing will be there, but during the period of mixing, you have to also apply the ultrasonic waves.
Sir, 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 sir.
So that will avoid the formation of agglomerations.
Sir, sir. Sir, one point is that this 3 percentage by weight, the polymer,
Yes.
if I send it to a particular borosil test tube,
Okay.
so 3%, matlab 97 percentage by weight polymer, if I
Okay.
am sending it to the test tube, so volume of the 3% is occupying almost borosil test tube, sir. It is this much low density material. My point is that to take it to next level where it should be applicable, sir.
Next level means?
Like, sir, I am if I want to conduct some tests, so I need to find some applications. So it is a very low density. So in that direction, I am having curiosity, sir.
See, low density means weight will be less.
Yeah, yes, sir, yes, sir.
Okay.
Yes, sir.
So mainly the low weight applications are in the aircraft and the space.
Sir, sir.
Because now their main requirement is the saving of the weight. So
Sir,
even
sir.
if the material cost is high, they can go for it.
Sir, sir.
So you can identify a particular component which will where it can be used. But for that you have to also study the physical and mechanical properties of the
Actually, sir,
uh,
actually, I am preparing this composite in the borosil test tube itself. So it's the requirement of tribology sample, sir. So actually, I am doing tribology for that, sir. Apart from tribology, is there any application in sir?
See, that will depend upon application. See, I'll told you now. What generally how you decide the application? Application will depend upon the environment in which you are going to use the component. Okay.
Yes, sir. Yes, sir. Yes, sir.
Now, how you will decide the environment? So first you have to test your specimen which you are making. Testing means in the moisture environment, in the heat minimum temperature, maximum temperature, then different mechanical test, hydrothermal test. So you have to find a range
Yes, sir.
of
Yes,
the
sir.
product which you are making.
Yes, sir.
Then you have to see the industrial requirement in that range.
Sir,
Then
sir.
only you can say where it will be useful.
Sir, 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 sir.
Hmm.
Sir,
Huh.
if I want any further discussion, can I communicate sometime, sir?
You can communicate. My email is there in the NIT Manipur website, Department of Mechanical. So you can
Sir,
drop
sir,
a
sir.
mail to me.
Yes, sir. Yes, sir. Thank you very much, sir.
Okay. Any other questions from some participants?
Yes, sir. I am having one question, sir.
Please.
Your presentation was very nice regarding the nanomaterials and the nanocomposite.
Okay.
What is your opinion about the nanotoxicity that will be a future problem?
Yes, nanotoxicity will be the future problem. That is true. But nanotoxicity will be a serious issue when the nanoparticles are dispersed freely in the environment. That will be the problem. Only when. But once you are embedding the nanoparticles in some matrix, means they are not fully released in the environment. So that is where we have to control it. Number one. Number two is whatever device is made. So some system is to be developed where you do not allow the nanoparticles to move freely in the environment. That is to be controlled. Nanocomposite, this problem will not be there because they are embedded in some matrix nanoparticles.
Okay.
Any other question? So if you don't have questions, I am closing my presentation.
Thank you very much, Professor Rajesh Kumar Bhushan, Dean Academics, NIT Manipur. So now it is the time for taking a quiz and finalize and finish the session for 5 days FDP program. I request all of you should join the Google Classroom because otherwise the result cannot be discussed. Okay. So result will recorded and everything will marked in the Google Classroom only. Please put your email ID and a name and email ID correctly so that it will reflect in the this what is called in the attendance, all these things. So I will mark it present or whatever maybe. So I will share this link in a Google platform. Please see the Google link and finish up this thing. Of course, there is some limitations over this thing in pandemic. So I what I expect that cannot be fulfilled. My talk and everything that is not fulfilled. So due to limitation of time and all these things. So is it okay? I thank to all participants to be who are attending in the 5 days program. Thank you very much. So there is already 110 participant is there, but in Google, this WhatsApp group, there is 114. I don't know how to settle down is there. So please cooperate these things. Someone is asking questions. Is it Dr. Pankaj Kumar Singh? Please. Do you have any questions?
No, sir. I've already asked, sir.
Sir, excuse me, sir. It is telling invitation not found. Actually, I opened the email to join the classroom.
No, there is no necessary of invitation. I have shared the Google Classroom link and a password. You can join without my consent also. Okay. Any other questions from other side? One by one, it will be better. Otherwise, it is rebound and make noise.
Sir, where is
Sir, please.
password and ID, sir, for joining the classroom?
Okay. So you didn't join.
Yes, sir. Yes, sir. I did not join, sir.
So you are in a WhatsApp group.
I don't have smartphone, sir. I'm sorry for that.
Okay. So actually, I have to write this thing, the Google link. Of course, I will give sufficient time. There is no problem.
Sir.
So anybody can share this link to, otherwise it will be very good for. So please share if it is anyone in the chat room.
Sir, I have a question
Okay, sir, I
for
will share
myself,
this.
Shweta, on this one.
Yeah, madam, please.
Sir, I am having my attendance through my official email ID, but while I was joining over there in the classroom, it was not accepting it. But while I using my normal email ID, which is not official, that is accepting. So what I will do, sir, during the examination?
Exam day, you have to join only Google link, classroom link. So this please join this thing, because we want result. Mark is important. So out of 30,
Okay, should I? Okay, over there, my name and everything will be there,
yes,
no?
your
So
name and email ID you can
email
write
ID.
there.
Okay.
Yes, yes.
Okay,
And
sir.
which
No,
institute you belongs. So that will reflect. Then I will arrange other things. So then that will be better for me.
Okay, sir. Thank you so much, sir.
So is there any problem, any query, all kind of things? Because please, now it is 3:30, around 3:30. So I expect B. Dhanalakshmi, do you have any question?
Yes, sir. Regarding the exam, regarding the quiz, I have a doubt, sir. Will it be in the form of a MCQ, sir?
All questions are MCQ, because I know that all are from faculties and from different disciplines.
Okay,
so due to this, I generalize these very simple questions. I think it is not necessary to attend these things. It is very simple questions.
Okay,
Just for because I know that you have faculty and you have lots of work. So workload. So this is the just I am very happy if you will enjoy these lectures. I don't know, because I didn't give this lecture here. Anyway, in future, if I will organize any FDP program once again, then of course I will give talk. So anyway, I am multidisciplinary and interdisciplinary faculty. So I am somewhat bio-related and nanoelectronics, then the computational. So little bit no, I am not expert in every field. Of course, this is I am very happy that at least 5 days program has finished, going to finish. And if you people are sign this Google Classroom and give the result, then I will at least submit these to ATAL AICT programs. Then the certificate will provide directly from that site. Okay, so that will better for this thing. So if any problem, please tell me now. Otherwise, if please.
So the question, whatever you are sharing with the Google Classroom, can you share in the chat box also? Because there is some problem in regarding the Google Classroom.
So this is the questions. Sorry.
Yes, yes, that the test link. Can you share in the WhatsApp group also?
There is already some links are already. Oh, I have to write this thing. Okay, I will try to this, because it is a link. I have to copy and paste. Okay, I will type these things.
Sir, I need your help, sir. Actually, I entered into the classroom. What is next, sir? Do I need to go to classroom, sir? Classwork.
Sir, I am not able to join it.
Join it means you are not registered. Did you join registered for this ATAL program? Hello, madam.
Sir, I am having one doubt, sir. I entered into the classroom, but I unable to find any questions, sir. Do I need to go to? Please tell me the procedure, sir.
No, I didn't share. I didn't share now. Now I will share it. Okay.
Sir. Yes, sir. Yes, sir.
So this question directly will go to these things. There is no problem. Okay. So now I am going to share. So please complete within the 2 hours time. That is sufficient, and the normal questions are there. Okay. So please do these things and automatic. Okay. Now I can assign.
The classroom.
Google phone. Google phone.
Sir, I am not able to enter the classroom.
Yeah. I understand.